Picture a city the size of Manhattan, but with the mass of our entire sun crushed into it. That's the mind-bending reality of a neutron star, one of the universe's most extreme and mysterious objects. These cosmic powerhouses are born from the explosive deaths of massive stars, packing unimaginable density into a sphere no bigger than a city. If that doesn't make your head spin, consider this. A single sugar cube-sized chunk of neutron star material would weigh as much as Mount Everest. And yet, as bizarre as these stellar remnants are, the ones lurking at the farthest edges of the observable universe hold secrets even more astonishing. You've probably seen neutron stars depicted in sci-fi collapsing into black holes, warping space-time, or even powering alien megastructures. But the truth is stranger than fiction. These distant neutron stars, some billions of light years away, are like cosmic lighthouses, pulsing with precision or unleashing magnetic fields so intense they could strip atoms apart from halfway across the galaxy. They challenge everything we think we know about physics, bending the rules of gravity, matter, and even time itself. And today, we're diving into 50 jaw-dropping facts about these enigmatic objects, facts that will redefine how you see the universe. From their role as cosmic gold factories to their ability to spin hundreds of times per second without tearing apart, neutron stars are the universe's ultimate survivalists. They're relics of supernovas so violent they outshine entire galaxies, yet they're also precise enough to rival atomic clocks. Some beam radiation like interstellar strobe lights, while others lurk in the shadows, invisible until they unleash bursts of energy brighter than a million suns. And the most distant ones, they're time capsules carrying clues about the early universe that we can't find anywhere else. So buckle up, we're about to journey to the farthest reaches of space, where the laws of physics break down and the stars themselves become the strangest stories ever told. Here's something that will put the universe into perspective for you. When a massive star, at least 8 times heavier than our sun, reaches the end of its life, it doesn't just fade away. It goes out with a cataclysmic bang, exploding in a supernova so powerful it can outshine an entire galaxy for weeks. But the real magic happens in the aftermath. What's left behind isn't just a smoldering husk, it's a neutron star, an object so dense it defies comprehension. Imagine taking the entire mass of our sun, all 2 octillion tons of it, and crushing it down into a sphere no wider than Manhattan. That's the reality of a neutron star. The gravitational forces at play here are so intense that atoms themselves can't survive. Electrons and protons are squeezed together until they fuse into neutrons, creating an ocean of subatomic particles packed tighter than anything else in the known universe. A single sugar cube's worth of this material would weigh 1 billion tons, enough to flatten mountains under its own weight. But the strangeness doesn't stop there. The gravity of a neutron star is so strong it bends space-time itself, warping the very fabric of reality around it. Light passing near its surface doesn't travel in a straight line, it curves, twisted by the star's immense pull. If you could stand on its surface, which of course you couldn't, time itself would move slower for you than for someone watching from a distance. It's like something straight out of a sci-fi novel, except this is real astrophysics. And the most distant neutron stars, their extreme properties are even more exaggerated, pushing the limits of what we thought was possible. The sheer power of a neutron star's gravity is beyond anything we can experience here on Earth. It's not just stronger, it's in an entirely different league. Picture this: the gravity at the surface of one of these cosmic beasts is a staggering 100 billion times more intense than what we feel on our planet. To put that incomprehensible number into perspective, imagine dropping something as soft and light as a marshmallow onto its surface. The moment it touches down, the impact wouldn't be a gentle splat. It would release energy equivalent to multiple atomic bombs, vaporizing instantly under forces that rewrite the rules of physics as we know them. This isn't just about crushing objects, it reshapes reality itself. The gravity is so overwhelming that even light struggles to escape, bending and twisting as it tries to flee the star's clutches. If you were somehow able to hover near the surface, an impossible feat, of course, the difference in gravity between your head and feet would be so extreme it would stretch you into a strand of atoms in milliseconds. This phenomenon, called spaghettification, is usually associated with black holes, but neutron stars flirt with the same terrifying extremes. And here's where it gets even wilder. This crushing gravity isn't just a destructive force, it's a cosmic sculptor. It alters the very way neutron stars emit light and radiation, creating bizarre observable effects. Some pulse like precision cosmic clocks, their beams of radiation sweeping across space like interstellar lighthouses. Others warp the space around them so severely that they create gravitational lenses, bending light from stars behind them into eerie rings. These extreme conditions make neutron stars laboratories for testing the laws of physics under conditions we could never replicate on Earth, pushing our understanding of matter, energy, and the fabric of space-time to the breaking point. Now take the mind-boggling density of a neutron star and set it spinning faster than a kitchen blender on its highest setting. Except we're talking about an object with the mass of a sun whirling hundreds of times every single second. These cosmic speed demons are called pulsars, and they're neutron stars that don't just sit quietly in space. They rotate with such ferocious speed that their surfaces can move at nearly a quarter the speed of light. Picture a skater pulling their arms in during a spin, but instead of speeding up gracefully, this stellar remnant revs up to 700 rotations per second, flinging out beams of radiation so intense they sweep across galaxies like interstellar searchlights. What keeps these objects from tearing themselves apart under such extreme forces? It all comes down to that unimaginable density we talked about earlier. A neutron star's gravity is so overpowering that even at these dizzying speeds, its surface holds together, warping inward rather than flying outward. But here's where things get even wilder. That rotation isn't just for show. As the star spins, its ridiculously powerful magnetic field whips around with it, accelerating particles to near light speeds and launching twin jets of radiation from its poles. When one of those beams happens to point toward Earth, we detect it as a rapid-fire pulse of energy, like a cosmic strobe light blinking with precision that rivals our most accurate atomic clocks. The energy behind these pulses is almost beyond comprehension. A typical pulsar's beam packs enough punch to outshine our entire sun, all concentrated into a narrow ray that sweeps past us in milliseconds. Some of these spinning powerhouses, called millisecond pulsars, have become so finely tuned over billions of years that their pulses arrive with clockwork regularity, varying by less than a microsecond over decades. Astronomers actually use them as galactic GPS markers, their steady beats helping map the structure of the Milky Way. And the fastest ones, they're nature's ultimate centrifuges, spinning so rapidly that if you stood on their surfaces, impossible as that would be, you'd experience forces strong enough to compress atoms into spaghetti strands within nanoseconds. But perhaps the most astonishing thing about these whirling dervishes is how they form in the first place. When a massive star collapses into a neutron star, it conserves all the angular momentum of its former self, like an ice skater pulling in their arms, but starting with a star originally millions of miles across. The result is a stellar remnant spinning at speeds that push the limits of physics, often with magnetic fields trillions of times stronger than Earth's. These aren't just dead stars, they're cosmic dynamos, converting rotational energy into radiation with efficiency that would put any human-made power plant to shame. And out in the farthest reaches of the universe, where conditions are even more extreme, some pulsars may be spinning faster than we've ever detected, their pulses stretched and redshifted by the expanding cosmos before they ever reach our telescopes. If you thought neutron stars couldn't get any more extreme, meet their terrifying cousins Magnetars. These cosmic monsters take the already mind-bending physics of neutron stars and crank it up to 11, boasting magnetic fields so powerful they could dismantle matter itself from halfway across the solar system. We're talking about magnetic forces a quadrillion times stronger than Earth's, enough to warp the very structure of atoms in ways that would make even the most hardened physicist shudder. Picture this: a magnetar's magnetic field is so intense that if you somehow found yourself within 1,000 miles of one, every electron in your body would be violently rearranged. The field strength would distort the electron clouds around atoms, stretching them into needle-thin shapes until the chemical bonds holding you together simply unravel. Your credit card's magnetic strip wiped clean instantly, your smartphone's data obliterated in a nanosecond. Even starships from sci-fi fantasies wouldn't stand a chance. Their hulls would be torn apart at the molecular level long before they got close enough to see the wreckage. But the true horror of these fields isn't just their destructive power, it's how they warp the very fabric of space. The magnetic forces are so overwhelming that they twist the quantum vacuum around the star, creating a bizarre zone where empty space itself becomes unstable. Photons traveling through this distorted region can't even move in straight lines, they split apart, a phenomenon called vacuum birefringence, which scientists once thought was impossible outside of black holes. And then there are the starquakes, cataclysmic fractures in a magnetar's crust caused by the unimaginable strain of its own magnetic field. When these quakes hit, they release energy bursts so powerful they briefly outshine every star in our galaxy combined. In 2004, a magnetar eruption 50,000 light-years away was so intense it temporarily ionized Earth's upper atmosphere, despite being halfway across the Milky Way. That's like a campfire on the moon burning your eyebrows off. Yet for all their destructive potential, magnetars might hold the key to one of astrophysics' greatest mysteries: fast radio bursts, those enigmatic cosmic signals that have puzzled scientists for years. Some researchers now believe these fleeting but powerful pulsars could be the death screams of distant magnetars, their magnetic fields snapping like cosmic rubber bands and releasing as much energy in a millisecond as our sun does in 3 days. So while we should be grateful these magnetic monsters are rare and far away, we should also be fascinated they're pushing our understanding of physics to its absolute limits, revealing a universe far stranger than we ever imagined. Deep in the constellation Ursa Major, there's a flicker of radiation so faint it barely registers on our most sensitive telescopes, yet it carries a message from when the universe was just a toddler. Meet PS1 J000 plus 02142, the most distant neutron star ever detected, beaming its whispers to us from a staggering 13 billion light-years away. That means the light we're seeing now left this cosmic relic when the universe was less than 800 million years old, a mere blink after the Big Bang. Detecting something this far away is like spotting a single candle flame on the moon during a thunderstorm. Neutron stars are already challenging to observe at cosmic distances. Their small size and often erratic emissions make them elusive targets. But PS1 J00 plus 02142 is special because it wasn't just quietly fading into the void. It erupted in a gamma-ray burst, one of the universe's most violent explosions, briefly outshining entire galaxies and leaving behind an afterglow that astronomers could trace back to its origin. What makes this discovery so groundbreaking isn't just the distance, it's the implications. This neutron star existed during the cosmic dawn, a period when the first stars were still lighting up the darkness. Its very presence challenges our understanding of how quickly stellar evolution occurred after the Big Bang. Normally, it takes hundreds of millions of years for massive stars to form, live, and die in supernova that leave behind neutron stars. Yet here we have evidence of one that did it all in record time, like a cosmic overachiever racing against the infancy of the universe itself. The journey of its light to reach us is a story of cosmic endurance. Those photons spent 13 billion years stretching across an expanding universe, dodging galaxies and gas clouds, their wavelengths reddening until they were barely detectable by the time they reached Earth. And here's the wildest part: the actual neutron star is likely long gone by now. Given the extreme environment of the early universe, it may have collapsed into a black hole or been torn apart by galactic collisions eons ago. We're essentially watching its final act, a ghostly encore from the edge of space-time. Yet despite these challenges, finding PS1J00 plus 02142 gives us something priceless, a snapshot of the universe's formative years. Its composition, magnetic field, and explosive behavior hold clues about the primordial conditions that shaped the cosmos. Every pulse of radiation we detect is like a time capsule, carrying secrets from an era when the first heavy elements were being forged in the hearts of exploding stars. This isn't just astronomy, it's cosmic archaeology, and we've just uncovered one of the rarest relics in existence. When a massive star dies, it doesn't just collapse quietly into a neutron star, it gets violently evicted from its cosmic neighborhood. These stellar remnants don't just sit where they're born, they're often hurled into the void at speeds that defy imagination, some reaching up to 5 million miles per hour. This cosmic ejection is called a natal kick, and it's one of the universe's most dramatic exit strategies. Picture a supernova explosion so asymmetrical that it doesn't just blow off the star's outer layers. It effectively acts like a rocket engine, launching the newborn neutron star across the galaxy. The physics behind this is staggering. During the collapse, if more material is blasted outward in one direction than another, the conservation of momentum sends the neutron star recoiling in the opposite direction like a bullet from a gun. Some of these kicked stars move so fast they'll eventually escape their galaxies entirely, destined to drift forever in the emptiness between galaxies. Take the case of the neutron star known as CTX-1090, clocked racing through space at nearly 2.5 million miles per hour. It's moving so fast that it's already left a visible trail of shocked gas in its wake, like a speedboat churning up water. Or consider PSRB 2224+65, which astronomers nicknamed the Cosmic Cannonball. It's tearing through the Milky Way at such breakneck speed that it will inevitably break free from the galaxy's gravitational grip within a few million years. But what's even wilder is what these runaway stars leave behind. The force of their kicks often disrupts the surrounding nebula, twisting what should be a symmetrical debris field into chaotic tendrils. Some neutron stars even rip binary partners apart mid-flight, leaving a trail of orphan stars and scattered planetary wreckage. And because they're so dense, their gravity can yank nearby stars or gas clouds along for the ride, creating bizarre, elongated streams of matter in their path. These rogue travelers aren't just curiosities, they're time capsules. By tracing their paths backward, astronomers can piece together the violent histories of ancient supernova, some of which exploded before Earth even formed. And because they're ejected so early in their lives, these hypervelocity neutron stars offer a pristine look at the conditions right after a supernova, untouched by the interstellar medium that typically alters older remnants. So while neutron stars might seem like stationary beacons in sci-fi, the truth is far more dynamic. The universe doesn't just create these extreme objects, it launches them into the void like cosmic pinballs, leaving trails of mysteries in their wake. Think mountains on Earth are impressive. On a neutron star, the landscape is just as extreme but scaled down to something you could literally trip over. These cosmic remnants have what astronomers call mountains, but don't picture towering peaks. These surface imperfections might only rise a few centimeters tall. Yet that tiny bump, no taller than a coffee mug, packs more mass than Mount Everest. Here's why: neutron star gravity is so intense that it flattens any significant elevation instantly. The same forces that crush atoms into neutron soup won't allow anything to protrude more than a few centimeters before it collapses under its own weight. Imagine trying to build a sandcastle on the surface of a black hole. That's the kind of futility we're talking about. Even so, these minuscule deformations aren't just curiosities. They're the result of the star's ridiculously rigid crust, a lattice of atomic nuclei so densely packed that it's 10 billion times stronger than steel. But here's the mind-blowing part. These mountains aren't stationary. As the neutron star spins sometimes hundreds of times per second, those tiny imperfections whip around, creating ripples in spacetime itself. Gravitational waves, those cosmic tremors predicted by Einstein, are emitted with every rotation, carrying energy away from the star. The faster the spin, the more these microscopic bumps distort the fabric of reality around them. Some neutron stars lose rotational energy so efficiently through gravitational waves that their mountains might be literally shaking themselves apart over millennia. What's wild is how we detect these effects. When gravitational wave observatories like LIGO catch the faintest whispers from colliding neutron stars, they're partly sensing the ghosts of these surface imperfections. Even a centimeter-high mountain, if suddenly flattened during a collision, would release more energy than our sun emits in 1,000 years, and some theories suggest that the hottest, youngest neutron stars might have taller mountains, maybe even up to 10 centimeters before gravity inevitably smashes them down into submission. So while Earth's mountains take millions of years to erode, neutron star mountains live fast and die hard. Their fleeting existence is a battle between unimaginable density and the universe's subtle tremors, proving once again that in space, even the smallest features can have cosmic consequences. Digging deeper into a neutron star's core is like descending into a cosmic kitchen gone mad, one where atomic nuclei are crushed into shapes that would make an Italian chef weep. Scientists call this bizarre matter nuclear pasta, not because they're hungry, but because the extreme pressures here warp atomic structures into forms resembling spaghetti strands, lasagna sheets, and even gnocchi like clumps. It's the densest and strangest matter in the universe, packed so tightly that protons and neutrons lose their individuality entirely, merging into a quantum soup where the rules of physics as we know them start to break down. The recipe for this cosmic dish begins about a kilometer beneath the star's surface, where gravity's grip becomes so overwhelming that atomic nuclei can't maintain their usual spherical shapes. Instead, they're stretched into long, thin filaments, the so-called spaghetti phase. Go deeper, and these strands get pressed together into layers, forming lasagna sheets of nuclear material. Near the very core, the pressure becomes so absurd that these sheets fragment into dense, lumpy clusters, the gnocchi phase. Each of these structures is unimaginably strong, with a single cubic centimeter weighing more than all the skyscrapers on Earth combined. What's wild is how this nuclear pasta might influence the star's stability. Those gnocchi-like chunks could act like speed bumps in the star's superfluid core, resisting the flow of neutrons and creating internal friction. Some theories suggest this might lead to starquakes, sudden shifts in the crust that release bursts of energy detectable across the galaxy. Others propose that the pasta phases could trap magnetic fields in twisted configurations, explaining why some neutron stars have magnetic flares powerful enough to ionize planets light years away. Even stranger, this matter might be so dense that it temporarily halts the collapse toward a black hole, giving neutron stars their cosmic staying power. Simulations show these pasta structures could be tougher than any material we know, potentially holding up under stresses that would instantly crush diamond into oblivion. Yet if the conditions tip just slightly, perhaps from a collision or gradual mass accumulation, the entire structure could shatter in a catastrophic phase transition, collapsing into a black hole in milliseconds. The real challenge will likely never directly sample this matter. The pressures required to create nuclear pasta are 100 trillion times what we can produce in labs, making it a theoretical playground for physicists. But by studying the way neutron stars vibrate, cool, and emit radiation, we're piecing together clues about this alien physics happening right under their surfaces. It's a reminder that even in the most extreme corners of the universe, nature finds ways to surprise us, crafting structures so strange they blur the line between particle physics and culinary art. Even the most precise cosmic clocks sometimes skip a beat, and when a neutron star does it, the results are spectacular. These hiccups, called glitches, are sudden surges in a pulsar's rotation speed, as if the universe itself hit the fast-forward button. Picture a spinning ice skater who inexplicably speeds up without pulling their arms in. That's the kind of cosmic defiance we're talking about. The Vela pulsar, one of the most studied neutron stars, has treated astronomers to multiple glitches over the decades, each one revealing tantalizing clues about the chaotic physics churning beneath its surface. So what's behind these bizarre events? One leading theory points to starquakes, violent fractures in the neutron star's rigid crust. Imagine the crust as a brittle shell floating atop a superfluid core. As the star gradually slows down over millennia, the crust warps under immense strain until crack. It suddenly shifts like tectonic plates on Earth. This releases pent-up energy, briefly accelerating the star's spin. The Vela pulsar's glitches often involve jumps equivalent to gaining a full rotation every few years, crammed into mere seconds. But there's another, even stranger possibility: superfluid vortices breaking free. Deep inside a neutron star, protons and neutrons may swirl in frictionless quantum whirlpools. Normally, these vortices are pinned in place by the crust's magnetic field, rotating in sync. But when too many build up, they can suddenly unpin and surge outward, transferring their momentum to the star like a cosmic slingshot. It's as if the star's interior has a mind of its own, occasionally rebelling against the rigid order of the surface. The Vela pulsar's most dramatic glitch, recorded in 2016, saw its spin rate spike by 1 part in a million in less than 12 seconds. For an object that typically slows down with metronomic predictability, this was like watching a grandfather clock suddenly sprint ahead, even more intriguing. Some glitches come with eerie electromagnetic aftereffects, flares of X-rays or radio waves hinting at unseen turmoil beneath the crust. These events aren't just quirks, they're cosmic experiments. Each glitch peels back another layer of mystery about neutron star interiors, where matter exists in states we can't replicate anywhere in the universe. And while we've catalogued hundreds of glitches across the galaxy, the sheer variety suggests there's no single explanation. Some neutron stars might glitch quietly, while others, like the erratic J0835-4510, experience violent spin changes followed by years of eerie calm. What's clear is that beneath their polished clockwork exteriors, neutron stars harbor chaos, and every unpredictable leap reminds us that even in the cold depths of space, nature still has surprises up its sleeve. At the scorching surface of a neutron star, where gravity could flatten mountains into pancakes, there exists something almost delicate, an atmosphere so thin it would shame a laboratory vacuum. Unlike Earth's blanket of air stretching for miles, these stellar remnants sport gaseous layers barely thicker than a pencil lead, often just a few millimeters hugging their unthinkably dense surfaces. Yet these whisper-thin veils of hydrogen or carbon aren't just cosmic curiosities, they're X-ray factories, superheated to millions of degrees by the star's relentless radiation and crushing magnetic fields. Picture Earth's atmosphere as a deep ocean, then imagine replacing it with a single sheet of tissue paper. That's the scale we're dealing with here. But what these neutron star atmospheres lack in thickness, they make up for in sheer violence. The hydrogen or carbon atoms trapped in this layer don't float gently like our air molecules. They're pummeled by particles accelerated to near light speeds, creating a frenzied soup of ionized plasma. When these charged particles collide, they emit X-rays so intense they can be spotted across interstellar distances, flashing like cosmic beacons against the void. Detecting these signals is like trying to study a candle flame from orbit during a hurricane. Earth's thick atmosphere absorbs X-rays, forcing astronomers to rely on space telescopes like Chandra or XMM Newton. These instruments don't just snap pictures, they act as cosmic spectroscopes, dissecting the faint X-ray glow for clues about the atmosphere's composition and behavior. Some neutron stars show absorption lines suggesting carbon atmospheres, while others reveal bizarre quantum effects where the thin gas acts more like a solid due to the star's ridiculous magnetic fields. The real marvel is how these wispy layers survive at all. With surface gravity 100 billion times Earth's, you'd expect every atom to be immediately crushed into oblivion. Yet some neutron stars manage to maintain these fleeting atmospheres through a combination of magnetic confinement and constant replenishment, either stealing gas from companion stars or slowly evaporating material from their own crust. It's a precarious balancing act, like trying to hold onto a cloud of smoke in a tornado. And when these atmospheres do flare up, the results are spectacular. Some neutron stars exhibit X-ray bursts where their thin gaseous layers suddenly ignite, increasing in brightness by a factor of 1,000 in seconds before fading again. These aren't just pretty light shows, they're extreme physics experiments, revealing how matter behaves when pressed to its absolute limits. So while a neutron star's atmosphere may be the universe's most modest cloak, it's also one of its most revealing, a fleeting whisper of gas that shouts volumes about the brutal conditions just millimeters below. Most neutron stars exist in the distant reaches of deep space, but one cosmic recluse defies expectations by lurking practically in our backyard just 400 light-years away. Nicknamed Calvera after the villain from the Magnificent Seven, this isolated neutron star sits uncomfortably close to Earth, challenging everything astronomers thought they knew about where these stellar corpses should reside. At that distance, if it were a typical pulsar, its radiation would be strong enough to light up our night sky like a faint but persistent strobe. Yet Calvera remains mysteriously quiet, emitting only a whisper of X-rays, a trait that makes it even more puzzling. How did a neutron star end up so close without us noticing sooner? The leading theory suggests Calvera is a throwaway from a binary system kicked out by its companion star's supernova explosion like a cosmic slingshot. Normally, such violent ejections send neutron stars racing through the galaxy, but Calvera seems to have gotten barely any kick at all. It's drifting through space at a leisurely pace, as if it barely noticed the explosion that birthed it. Stranger still, most isolated neutron stars this age should have cooled into near invisibility by now. Yet Calvera remains just warm enough to detect, hinting at some unknown heating mechanism under its surface. What really baffles scientists is the star's loneliness. Neutron stars usually form in dense stellar nurseries or cling to companion stars, but Calvera floats completely alone in a region of space that's practically empty, a celestial ghost haunting the edges of our cosmic neighborhood. Its isolation suggests it might belong to an entirely new class of neutron stars, one that forms under rare conditions we've yet to understand. Some researchers speculate it could be the remnant of a failed hypernova, a supernova so weak it barely made a splash, while others propose it's a rare, accretion-powered neutron star, slowly feeding on interstellar gas to stay warm. But here's the real kicker: Calvera might not be alone. If one neutron star exists this close, there could be dozens more hiding in the darkness, invisible to our telescopes until they flare up or drift into detection range. That raises a spine-tingling possibility our solar system might have had close encounters with these cosmic bullets in the past, and we'd never know unless one suddenly woke up. Calvera's quiet presence is a reminder that even in the quietest corners of space, the universe keeps its most explosive secrets. Beneath the chaotic surface of a neutron star lies a crust unlike anything in our solar system. A crystalline lattice so dense it makes diamond look like tissue paper. This isn't just strong material, it's matter pushed to its absolute limit, with bonds between atomic nuclei 10 billion times more resilient than steel. The pressure here is so intense that protons and electrons have long since merged into neutrons, leaving behind a skeletal framework of pure atomic nuclei spaced just femtometers apart. Picture the entire Eiffel Tower compressed down to a sugar cube, then reinforced with forces beyond human engineering. That's the neutron star's crust. But this ultra-dense armor isn't indestructible. When the star's insane magnetic field strains against it or the superfluid core beneath shifts unpredictably, the crust cracks under the pressure not with a whimper, but with a violence that sends shockwaves through space-time itself. These are starquakes, cosmic tremors so powerful they can briefly realign the entire star's magnetic field. The energy released when even a centimeter-thick section fractures is equivalent to a magnitude 32 earthquake, enough to send detectable ripples through the fabric of the universe. Some of these quakes trigger the mysterious glitches we observe in pulsars, where the star suddenly spins faster as pent-up energy from the core surges outward. The physics behind these fractures reads like science fiction. Unlike Earth's tectonic plates that slide gradually, neutron star crusts fail catastrophically. Think of a frozen lake shattering all at once rather than cracking slowly. The crystalline structure snaps with such force that it launches relativistic particles into space, creating flares visible across the galaxy. Meanwhile, deeper layers of the crust exhibit bizarre quantum behaviors, with nuclei arranged in shapes resembling cosmic pasta, spaghetti-like strands, and lasagna sheets that vibrate at frequencies we can barely model. These events aren't just dramatic displays, they're gold mines for astrophysicists. Every starquake broadcasts information about the crust's composition through gravitational waves, subtle ripples carrying fingerprints of the star's internal structure. By studying these signals, researchers have deduced that the crust isn't uniform. It likely has mountain ranges microscopic by our standards that create asymmetries in gravitational wave emissions. The 2017 detection of colliding neutron stars by LIGO revealed how crust material gets flung into space during impacts, enriching the cosmos with heavy elements like gold and platinum. Yet for all its strength, this crust is really just a fragile skin over unimaginable forces. The superfluid neutrons beneath it move with zero friction, creating currents that constantly tug at the rigid surface. Magnetic field lines frozen into the crust during the star's birth act like cosmic winches, twisting sections of the surface until something gives way. It's a perpetual battle between structure and chaos, where the universe's strongest known material regularly meets its breaking point, and in doing so, reveals secrets about the extreme physics governing these stellar remnants. Some neutron stars aren't content with being lonely relics. They become cosmic thieves, robbing their stellar neighbors in a gravitational heist that would make any outlaw jealous. In binary systems where a neutron star orbits a companion, often a hapless sun-like star, or even a massive supergiant, the pull is so immense it can yank gas straight from its partner's atmosphere. This stolen material doesn't just vanish. It spirals into a glowing, superheated disk around the neutron star, a cosmic whirlpool called an accretion disk where temperatures soar to millions of degrees. The violence of this process is staggering. As gas from the donor star funnels toward the neutron star's surface, it accelerates to nearly light speed, emitting intense X-rays that pulse like a strobe light. Some systems, dubbed X-ray binaries, flare so brightly they outshine entire galaxies in this high-energy light. But here's where it gets even wilder. When enough stolen matter piles up on the neutron star's surface, it triggers thermonuclear explosions so powerful they vaporize entire mountain ranges worth of material in seconds. Astronomers call these events X-ray bursts, and they're some of the most energetic phenomena in the universe. Packing more power than our sun will release in a week into a fireball that lasts barely a minute. What's fascinating is how this theft changes both stars forever. The donor star, slowly drained of its outer layers, can become a bizarre, stripped-down remnant, either a helium star or even a white dwarf orbiting uncomfortably close to its predatory partner. Meanwhile, the neutron star grows heavier with each stolen bite, inching closer to the theoretical limit where it might collapse into a black hole. Some of these binaries, like the famous Scorpius X1, have been feasting for millions of years, their accretion disks glowing so brightly they're visible across interstellar distances. But the real spectacle happens when the stolen gas carries a magnetic field with it. As this magnetized plasma crashes onto the neutron star's surface, it can realign the star's own monstrous magnetic field, triggering sudden flares that ripple through the accretion disk. These outbursts can temporarily make the system thousands of times brighter, illuminating nearby dust clouds like a cosmic spotlight. And in extreme cases, the infalling matter might even be the key to resurrecting dead pulsars, their spin rates revving back up as the stolen gas transfers angular momentum, turning once quiet neutron stars back into whirling dynamos. This gravitational piracy isn't just destructive, it's creative. The violent collisions in the accretion disk forge heavy elements like gold and uranium, scattering them into space when the disk occasionally overflows. Some scientists believe these binary systems could be the universe's primary factories for rare earth metals, their stolen matter transformed into cosmic treasure. So while the neutron star might be the ultimate celestial predator, its appetite also seeds the galaxy with the very materials that make planets and life possible. Not all pulsars announce their presence with the familiar radio wave beacons. We often imagine some broadcast their pulses in an even more extreme language, gamma rays, the highest energy light in the universe. These aren't just slightly more energetic versions of radio pulses. They're a completely different beast, generated through mechanisms so violent they make the radio emissions look gentle by comparison. The Fermi Gamma Ray Space Telescope has catalogued hundreds of these gamma-ray pulsars since its launch in 2008, revealing a hidden population of neutron stars that shine brightest in light our eyes were never meant to see. So why the dramatic difference in wavelengths? It all comes down to location. Radio pulses typically originate from the neutron star's magnetic poles, where charged particles spiral along field lines and emit coherent beams. Gamma rays, however, are born much farther out, where the star's magnetic field whips particles to near-light speeds in a zone called the outer gap. Here, electrons and positrons collide with such force that they convert their kinetic energy directly into gamma-ray photons, creating flashes far more energetic than anything the radio-emitting regions can produce. The Fermi telescope catches these gamma-ray pulses as rhythmic flashes, sometimes hundreds per second, each packing more punch than the entire output of our sun. Unlike radio pulses, which tend to be narrow and precise, gamma-ray pulses are often broader and more chaotic, their light curving through the star's twisted magnetic environment before escaping. Some of these pulsars, like the famous Geminga, are virtually silent in radio waves yet blaze like cosmic lighthouses in gamma rays, suggesting that what we traditionally think of as a pulsar might just be one facet of a much more complex phenomenon. What's truly fascinating is how these gamma-ray pulsars challenge our understanding of neutron star evolution. Many of them are middle-aged billions of years old, yet still produce gamma rays efficiently, defying expectations that pulsars should turn off as they age. Some researchers think this sustained activity comes from their magnetic fields interacting with debris disks or interstellar material, while others propose that the outer gaps simply take longer to dissipate than the polar radiation zones. Either way, these high-energy pulsars remind us that neutron stars don't fade quietly. They go out kicking and screaming, their gamma-ray pulses etching their final cosmic signatures across the void. Touching the surface of a neutron star would vaporize you instantly, not just from the crushing gravity, but from heat so intense it makes the sun's surface feel lukewarm. Clocking in at around 1 million degrees Celsius, these stellar remnants blaze with temperatures that could melt through tungsten like butter. To put that in perspective, our sun's visible surface simmers at a relatively tame 5,500 degrees, barely 0.5% as hot. Yet neutron stars achieve these staggering temperatures without nuclear fusion, burning instead with the lingering fury of their catastrophic birth. When a massive star collapses into a neutron star, the energy released isn't just in the supernova blast, it's bottled up inside the newly formed core. Imagine taking all the heat from a star's entire lifetime and compressing it into an object the size of a city. That trapped thermal energy has nowhere to go but out, leaking slowly over hundreds of thousands of years through the only available escape, X-rays. These high-energy photons pierce through the star's thin atmosphere, carrying away its warmth at a glacial pace. Some younger neutron stars, like the famed Cassiopeia, a remnant, still glow fiercely in X-ray images, their surfaces searingly hot just 300 years after their explosive birth. But here's the puzzle. Even the oldest neutron stars, those that should have cooled to near absolute zero by now, still radiate detectable X-ray warmth. The secret might lie beneath their crusts, where exotic particles or residual nuclear reactions could be generating heat against all odds. Some theories suggest that friction between the superfluid core and the crystalline crust acts like a cosmic battery, while others propose that decaying magnetic fields convert energy into heat like an interstellar induction stove. The Sun, by comparison, is a temporary furnace, its heat sustained by ongoing fusion reactions that will eventually sputter out. A neutron star's warmth, though, is the ember of a fire that's already burnt out, lingering far longer than anyone expected. And as those X-rays slowly bleed into space, they carry with them the fading echo of one of the universe's most violent acts, a reminder that even in death, stars refuse to go quietly. Sound travels differently inside a neutron star than anywhere else in the universe, not as a gentle wave, but as a supersonic shock ripping through matter at half the speed of light. This isn't the sound you know. It's vibrations moving through a quantum sea of degenerate neutrons packed so tightly they behave like a single, ultra-dense fluid. Under these extreme conditions, the usual rules of acoustics shatter. A whisper here would cross the star's 20-kilometer core in less than a millisecond, faster than a bullet but still lagging behind the mind-bending physics at play. The secret lies in how neutron star matter responds to pressure. In normal materials, sound moves by atoms bumping into each other, limited by their spacing and bond strength. But in a neutron star's core, atomic nuclei have been obliterated. What remains is a near-frictionless neutron superfluid threaded with protons moving like electric currents. Squeeze this substance and it pushes back with unbelievable stiffness, allowing vibrations to propagate at relativistic speeds. It's like striking a diamond with a hammer, except the diamond is 100 trillion times harder, and the hammer blow travels at 60,000 miles per second. This bizarre acoustics isn't just theoretical. When neutron stars collide, their cores ring like bells, emitting gravitational waves whose frequencies reveal the speed of sound inside. The 2017 detection of merging neutron stars by LIGO showed these waves oscillating at kilohertz frequencies consistent with sound zipping through their interiors at significant fractions of light speed. Some models even suggest the innermost core might host sonic black holes, regions where sound waves become trapped just like light in a gravitational singularity. Why does this matter? Because sound speed is a direct window into the star's deepest secrets. The stiffer the interior, the faster vibrations travel, hinting at whether quarks have broken free from their neutron prisons or if exotic particles like hyperons swirl in the mix. It's the difference between a neutron star having a uniform superfluid core versus layered phases of stranger matter. Each hypothetical state, from quark-gluon plasma to color superconductors, would leave its signature in the star's acoustic properties, like cosmic sonar mapping terrain we'll never see directly. So while we'll never hear these sounds, no medium exists to carry them through space. Their implications echo across astrophysics. They challenge our understanding of how matter behaves under conditions so extreme that even empty space becomes warped and unstable. And when the next neutron star collision lights up our detectors, the subtle vibrations hidden in its gravitational waves might finally answer which of these impossible theories is real. Einstein's theory of relativity predicted something extraordinary, that massive objects don't just sit in space, they warp the very fabric of reality around them. And neutron stars are among the most dramatic proof of this cosmic bending, acting like natural magnifying glasses that twist and amplify the light of stars behind them. When a neutron star aligns perfectly between Earth and a distant star, its incredible gravity doesn't just pull on matter, it distorts the path of starlight itself, curving it around the star in a phenomenon called gravitational lensing. The effect is like looking through the bottom of a wine glass. Background stars don't appear to shift slightly. They stretch into arcs or even complete rings of light encircling the neutron star. In 2013, the Hubble Space Telescope caught one particularly striking example near the neutron star RxJ 1856.5-3754, where multiple background stars appeared displaced from their true positions, their light bent like headlights viewed through fog. Some were stretched into tiny crescents, while others brightened unexpectedly as the neutron star's gravity focused their light toward Earth like a cosmic magnifying glass. What makes neutron star lensing so special isn't just the visual spectacle, it's the precision with which these observations match Einstein's century-old equations. The amount of bending depends exactly on the star's mass and how closely the light grazes its surface. For neutron stars, which pack a sun's worth of mass into such a tiny package, the lensing effects are incredibly pronounced even at small scales. Some pulsars have been observed momentarily brightening background stars by factors of 10 or more during perfect alignments, giving astronomers fleeting opportunities to study otherwise invisible celestial objects behind them. Gravitational lensing does more than just confirm relativity. It lets us weigh neutron stars directly. By measuring how much they deflect background light, scientists can calculate their masses with extraordinary accuracy, helping solve mysteries about how dense matter can truly get. In 2018, lensing measurements of the neutron star J0246-0730 revealed it was nearly twice the Sun's mass, ruling out certain theories about how matter behaves under extreme pressure. The most extreme lensing events occur when neutron stars pass directly in front of galaxies. In these rare cases, the entire galaxy's light gets warped into an Einstein ring, a perfect circle of distorted starlight surrounding the neutron star. While most observed Einstein rings come from massive galaxy clusters, neutron stars create miniature versions, offering snapshots of the universe's warped geometry on stellar scales. These cosmic mirages don't just showcase gravity's power, they turn neutron stars into tools, letting astronomers probe the distribution of dark matter around them by how it subtly alters the lensing pattern. So while neutron stars might be famous for their crushing densities and magnetic fury, their ability to bend light reveals something equally profound. They're not just objects in space, but sculptors of spacetime itself, twisting the universe's canvas in ways that continue to test and confirm our deepest theories of physics. Among the countless bizarre features of neutron stars, here's one that seems impossible at first glance. Some actually host their own planets. Take Pulsar B1257+12, a pulsar over 2,000 light-years away that stunned astronomers in the early 1990s when they found not one but 3 worlds orbiting it. This wasn't just unexpected, it defied everything we thought we knew about planet formation. How could anything survive the apocalyptic supernova that birthed the neutron star? And if nothing did, how did new planets emerge from such a radioactive, chaotic environment? The answer lies in cosmic resurrection. One theory suggests these pulsar planets might be the charred skeletons of former gas giants' planets that miraculously endured their star's explosive death. Imagine a Jupiter-sized world orbiting too close to a doomed star. When the supernova hits, the outer layers of the planet get blasted away, leaving behind a dense, rocky core that continues orbiting the newly formed neutron star like a cosmic phoenix. These zombie planets would be unlike anything in our solar system, scorched, irradiated, and likely tidally locked to their pulsar host, with one hemisphere perpetually bombarded by lethal radiation. But there's another, even wilder possibility these worlds might have formed from the ashes. After a supernova, debris often forms a disk around the neutron star, similar to the protoplanetary disks where regular planets are born. Except this disk isn't made of pristine gas and dust. It's a swirling soup of heavy elements forged in the explosion itself. Gold, uranium, and other rare metals that would be trace elements on Earth could become the building blocks of these second-generation planets. In PSRB 1257+12's case, computer simulations show its planets likely coalesced from such a disk within 100 million years after the supernova, creating a system where diamond-rich worlds could orbit a stellar corpse that periodically bathes them in deadly gamma rays. The extremes don't stop there. These pulsar planets experience time differently due to their host's gravity. A year on the innermost world of PSRB 1257+12 lasts just 25 Earth days, despite being 5 times closer to its neutron star than Mercury is to our Sun. And they're not alone. Dozens of similar systems have been found since, including one where a planet orbits a neutron star black hole binary, caught in a perpetual dance between two of the universe's most extreme objects. What's truly mind-blowing is that some of these worlds might even be habitable, at least in theory. The intense radiation from the pulsar would sterilize any surface life, but subterranean oceans could persist, heated by tidal forces as the planets flex under the neutron star's gravity. Microbial life might exist in these buried seas, feeding on chemical energy from radioactive decay, a scenario that turns science fiction into plausible astrophysics. So while we often picture planets orbiting calm, sun-like stars, the universe keeps reminding us it prefers variety. From diamond worlds circling pulsars to molten metalscapes shaped by gravitational tides, these survivors and rebirths prove that where there's matter and time, planets will find a way even in the most hostile corners of the cosmos. Even the most ferocious magnetic monsters in the cosmos can't stay powerful forever. Over millions of years, a neutron star's magnetic field, whether it's the apocalyptic strength of a young magnetar or the steadier pull of a pulsar, gradually weakens in a process called magnetic decay. This isn't like a battery running down. It's more akin to the universe's slow erasure of a cosmic fingerprint, as the very physics holding those impossible fields together begins to unravel. Take the difference between a newborn magnetar and an elderly pulsar. A freshly formed magnetar crackles with magnetic energy measuring around 10 quadrillion Gauss, enough to twist atoms into pretzel shapes from 100,000 miles away. Compare that to a middle-aged pulsar like the Crab Nebulas, whose mere 10 trillion Gauss field seems almost quaint by comparison. Yet given enough time, even that pulsar's magnetism will dwindle to a fraction of its current strength, joining the ranks of quiet neutron stars whose fields have faded to 1 billion Gauss or less. So why does this happen? The leading theory points to the star's interior as the culprit. Beneath that rigid crust, protons in the superfluid core are thought to form currents that sustain the magnetic field. But over millennia, these protons gradually lose energy, some leaking into the crust, others annihilating when they encounter stray electrons. Like a spinning top losing momentum, the magnetic engine slows, its once deafening roar fading to a whisper. The decay isn't always smooth. Some neutron stars experience sudden drops in magnetic strength during starquakes, when the crust fractures and reconnects field lines in new configurations. Others, particularly those stealing matter from companion stars, might temporarily revive their fields through fresh infusions of charged particles. But overall, the trend is inexorable. Given enough time, even the most magnetic beast becomes a shadow of its former self. This slow fading has cosmic consequences. As a neutron star's magnetism wanes, its ability to generate powerful beams of radiation diminishes. Pulsars gradually pulse less brightly. Magnetars stop producing catastrophic flares. Yet in this quiet phase, they reveal new secrets. Their cooled surfaces become visible to X-ray telescopes, offering glimpses of the exotic matter beneath. What begins as a spectacular death becomes, ironically, one of the universe's most patient disappearances, an eons-long dimming of cosmic fireworks. The universe has a way of balancing extremes, and magnetic decay is no exception. For every terrifyingly powerful young magnetar, there's the promise that time will sand down its sharp edges, leaving behind a quieter but equally fascinating relic, one that whispers rather than screams its secrets across the light years. When two neutron stars spiral toward catastrophe, they don't just crash, they unleash a cosmic alchemy lab capable of forging the universe's heaviest elements in seconds. The 2017 detection of gravitational wave event GW170817 gave humanity front row seats to this spectacular process, revealing how a violent merger 300 million light-years away scattered gold, platinum, and uranium across interstellar space like a celestial jeweler flinging treasures into the void. The moment of collision is beyond apocalyptic, as the stars, each packing a sun's worth of mass into a city-sized sphere, finally touch. Their cores merge at nearly light speed, generating temperatures exceeding 1 trillion degrees. The impact shreds their ultra-dense material into streams of neutron-rich matter, which then get bombarded by enough energy to transform simple atoms into heavy metals almost instantly. This runaway nuclear fusion, called rapid neutron capture or the R process, is nature's ultimate smithy, hammering lightweight elements into gold hundreds of times faster than stellar cores ever could. What follows is even more dazzling: a kilonova, an explosion distinct from ordinary supernova, where the ejected material glows with the eerie blue light of radioactive decay. The 2017 event's afterglow, observed by telescopes worldwide, confirmed theorists' predictions. Neutron star mergers are the universe's primary gold factories. Calculations suggest the collision produced over 10 Earth masses of gold alone, along with enough platinum to outweigh entire mountain ranges. But the real magic lies in the aftermath. Those freshly forged elements don't stay clustered, they're hurled outward at relativistic speeds, eventually seeding nearby gas clouds with the raw materials for future planets and perhaps life. Every gold ring on Earth likely contains atoms birthed in such cataclysms, meaning your jewelry isn't just metal, it's stardust refined through one of the cosmos' most violent processes. GW170817 wasn't a one-off event either. Ancient meteorites trapped in our solar system contain isotopic signatures matching our process production, proving these collisions have been enriching galaxies for billions of years. And with modern observatories now fine-tuned to spot them, we're on the verge of uncovering just how often these cosmic forges ignite, and how much of our world was built from their celestial fallout. Hurtling through our galaxy at an almost inconceivable speed, 1,100 kilometers every single second, the Black Widow pulsar isn't just breaking cosmic speed limits. It's rewriting them. Officially designated PSRB 1957+20, this neutron star moves so fast it could cross the entire United States in under 4 seconds, outpacing even the expansion of its own supernova remnant. At that velocity, gravity alone can't explain its breakneck pace. This pulsar likely received a catastrophic kick from an asymmetrical supernova explosion, turning it into a runaway bullet of degenerate matter streaking through the Milky Way. But speed isn't the only thing that makes the Black Widow extraordinary. Like its arachnid namesake, this pulsar has a deadly habit of consuming its companions. Orbited by a small, doomed star just 1% the mass of our Sun, it bombards its partner with relentless radiation, so intense it's literally evaporating the star into space. Each rotation blasts the companion with particle winds moving near light speed, stripping away gas layer by layer and leaving behind a ghostly tail of ionized material stretching across light years. Astronomers estimate the victim loses the equivalent of Jupiter's mass every 100 million years, a slow but inevitable cosmic dissolution. The Black Widow's backstory reads like a stellar thriller. Most likely born in a dense globular cluster, it may have been flung into interstellar space by gravitational interactions with other massive objects, a celestial game of pinball with the highest stakes. Now free of its birthplace, it races through the galaxy's sparse halo, its spin perfectly timed at 622 rotations per second. That dizzying speed, combined with its motion, means this pulsar isn't just running, it's pirouetting through the void like a hyperactive ballet dancer with a lethal embrace. What awaits this cosmic fugitive? Project its path forward, and the Black Widow's fate becomes even more dramatic. Given its current velocity, it's moving fast enough to eventually escape the Milky Way entirely. A lonely voyager drifting into intergalactic space, its pulses growing ever fainter as the distance widens. Before that happens, though, it might encounter other stars or gas clouds, each interaction potentially altering its trajectory or even providing fresh material to devour. One thing's certain, whether it ends its days as a solitary wanderer or collides with another object in a spectacular finale, the Black Widow pulsar will keep racing against the cosmos itself, a testament to the universe's capacity for both violence and awe-inspiring velocity. The deeper mystery is how many more like it exist. Current technology only lets us detect the closest and brightest of these speed demons, meaning the galaxy could be teeming with similar ultra-fast pulsars, their signals too faint or too redshifted to catch. Each one would carry its own story of ancient explosions, gravitational slingshots, and the chaotic processes that shape the lives and deaths of the universe's most extreme objects. For now, the Black Widow remains our premier example, a cosmic rebel whose very existence challenges what we thought possible about how stars move, evolve, and ultimately meet their end. Deep in the cosmos, some neutron stars pulse with such unerring precision they put the world's finest atomic clocks to shame. Take PSR J0437-4715, a millisecond pulsar spinning 300 times per second, its radio beams sweeping past Earth with timing so exact it varies by less than a microsecond over a decade. This isn't just impressive, it's a level of accuracy that makes cesium atomic clocks, the gold standard for timekeeping on Earth, look almost haphazard by comparison. What enables this cosmic precision? It starts with their ridiculous density. A neutron star's tightly packed matter creates an extraordinarily stable rotation, resisting the forces that typically cause celestial bodies to wobble or slow unpredictably. But millisecond pulsars like PSR J0437 take it further. They've been spun up to insane speeds by siphoning matter from companion stars, a process that smooths out irregularities like a potter refining clay on a wheel. The result is a natural timepiece so reliable that astronomers use these pulsars to create a galaxy-spanning GPS system, tracking their pulses to map positions across the Milky Way with pinpoint accuracy. Imagine navigating by the steady ticks of a dead star. That's exactly what projects like NAS, a neutron star interior composition explorer mission, are doing, using pulsar timing to test autonomous spacecraft navigation. By comparing arrival times of pulses from multiple neutron stars, a spacecraft could triangulate its position anywhere in the galaxy, no Earth-based signals required. Some researchers even envision a future where pulsar timing arrays act as interstellar lighthouses, guiding humanity's first voyages beyond the solar system. The applications go far beyond navigation. These celestial metronomes are testing Einstein's theories with unprecedented rigor. When gravitational waves ripple through space, they subtly alter the arrival times of pulsar signals, allowing arrays like the European Pulsar timing array to detect these cosmic ripples indirectly. Millisecond pulsars are so sensitive to spacetime distortions that they might soon reveal the background hum of supermassive black hole collisions across the universe. Yet perhaps their greatest marvel is how they redefine durability. While human-made atomic clocks require meticulous maintenance in controlled environments, millisecond pulsars have kept perfect time for billions of years, through supernova, galactic collisions, and the chaotic birth of planets. They're not just timekeepers, they're living relics of cosmic history, their steady beats encoding stories of gravitational waves, dark matter interactions, and the very fabric of spacetime itself. In their unyielding rhythm, we find both a tool for exploration and a reminder of the universe's hidden order. A neutron star's rotation tells the story of its life like the rings of a tree. Except instead of counting years, we measure the slowing cadence of its spin. Most of these cosmic lighthouses are born spinning furiously, some completing hundreds of rotations every single second. But over millennia, they gradually lose energy, their relentless beams of radiation acting like cosmic brakes that sap their rotational fury. This slowdown, called spin down, lets astronomers estimate a neutron star's age with surprising accuracy. Take the Crab pulsar, spinning 30 times per second, a far cry from the blistering 100 rotations per second it likely had when it formed in 1054. By tracking how much it slowed over centuries, we've calculated its age to within decades of historical records documenting its supernova. But nature loves exceptions. Some neutron stars cheat the spin-down timeline by stealing youth from their stellar neighbors. These recycled pulsars, often found in binary systems, get spun up to dizzying speeds by siphoning gas from a companion star. As matter spirals onto their surfaces, it transfers angular momentum like a cosmic merry-go-round, getting pushed faster with each new rider. The result: elderly neutron stars reborn as millisecond pulsars, whirling hundreds of times per second with the vigor of stellar toddlers. Pulsar J 1748-2446 holds the current record at 716 rotations per second faster than a kitchen blender on full power, despite likely being billions of years old. The contrast between these speedsters and their slower siblings reveals hidden chapters of cosmic history. Isolated neutron stars left to break against the interstellar medium usually follow predictable spin-down curves. But those with companions can undergo dramatic second acts, their rotation rates rewritten by gravitational theft. Some even transition between states, like the Black Widow pulsars that first feast on their partners, then spin down alone after evaporating them entirely. What's fascinating is how subtly these spin rates encode astrophysical secrets. The exact speed at which a neutron star slows hints at the strength of its magnetic field, the density of its surroundings, and even the state of matter in its core. A sudden glitch, a fractional speed up amid the long-term slowdown, might signal a starquake rearranging its internal structure. Meanwhile, the oldest isolated pulsars, spinning just once every few seconds, become cosmic chronometers, their leisurely pulses marking the passage of eons in a universe that never stops changing. So while spin-down generally traces a neutron star's journey from youth to senescence, the outliers, the rejuvenated, the binary dancers, the speed demons defying expectations remind us that in the cosmos, age is more than just a number. It's a story written in angular momentum, gravity, and the complex interplay between stellar corpses and the universe that shapes them. Beneath the unbreakable crust of a neutron star lies one of the universe's most bizarre liquid realms, an ocean unlike anything on Earth. Forget water and waves, this hypothesized layer is a seething sea of superfluid neutrons, a quantum soup where particles flow without friction, defying every intuition we have about how liquids behave. Picture trying to stir a cup of coffee that never slows down, where microscopic whirlpools could spin for millennia without losing momentum. That's the surreal physics at play just a kilometer or two beneath the star's surface. This neutron ocean isn't just sitting still. It's alive with currents that might shape the star's entire magnetic personality. Unlike Earth's oceans, which respond to wind and tides, this ultra-dense fluid dances to the tune of quantum mechanics and gravity. Protons scattered through the mix act like cosmic electrical wires, conducting charges that amplify magnetic fields to ludicrous strengths. Some models suggest these subsurface currents could explain why young neutron stars suddenly glitch, their rotation rates jumping as superfluid vortices break free and transfer momentum to the crust like a hidden engine kicking into gear. The parallels to Earth's oceans only go so far. While our planet sees influence climate through heat exchange, a neutron star's liquid layer regulates something far more extreme: magnetic apocalypses. When the crust fractures in a starquake, the superfluid beneath might slosh violently, rearranging magnetic field lines in ways that trigger gamma-ray flares visible across galaxies. It's like a tsunami, except instead of water, it's a wave of degenerate matter moving at relativistic speeds, capable of bending space-time as it passes. What's truly mind-bending is how thin this ocean might be, perhaps just meters deep compared to Earth's kilometers-thick seas. Yet it holds more mass than all our planet's water combined. The pressure here is so intense that neutrons pair up into Cooper pairs, a phenomenon normally seen in superconductors, allowing them to flow without resistance. This isn't just a theoretical curiosity. It could solve the puzzle of why some neutron stars cool faster than expected, as superfluid vortices carry heat outward with freakish efficiency. The wildest part, we're essentially guessing based on ripples in spacetime. When gravitational wave detectors catch neutron star collisions, the vibrations hint at how matter behaves in these hidden layers. A splash in this cosmic ocean might send tremors through the crust we can measure from millions of light years away. So while we'll never dive into these alien seas, their existence and their influence reminds us that even the most extreme objects in the universe have depths we're only beginning to fathom. The universe witnessed a seismic event in 2004 that redefined what we thought possible about cosmic violence. A Magnetar starquake so powerful it briefly flooded the Milky Way with gamma rays. SGR 1806-20, a hypermagnetic neutron star 50,000 light-years away, released a millisecond-long convulsion in its crust that outshone every star in our galaxy combined. The energy released was equivalent to the Sun radiating for 150,000 years, all compressed into a blink so fast you'd miss it if you blinked. This wasn't just a stellar tremor, it was the cosmic equivalent of the Earth's crust splitting from pole to pole in a single catastrophic instant. What causes such unfathomable ruptures? Picture a neutron star's crust as a brittle shell floating atop a chaotic sea knot of water, but of superfluid neutrons under unimaginable pressure. The crust itself is a lattice of iron nuclei packed so tightly they form a crystalline structure 10 billion times stronger than steel. Yet even this supermaterial has limits, as the Magnetar's twisted magnetic field strains against it. Like invisible hands wringing a cosmic dish rag, the crust builds tension until it violently snaps. The resulting starquake doesn't just crack the surface like Earth's quakes. It realigns entire magnetic domains, releasing pent-up energy that accelerates particles to near light speed. The 2004 event created something astronomers call a relativistic fireball, a shockwave of electrons and positrons surfing the star's magnetic field lines like cosmic surfboards riding a tsunami. For 30 milliseconds, this expanding shell collided with interstellar gas, generating the brightest gamma-ray flash ever recorded from our galaxy. The afterglow lingered for minutes, allowing telescopes worldwide to study the aftermath of what was essentially a magnetic reconnection event scaled up to apocalyptic proportions. Here's where the asteroid belt analogy clicks. Just as our solar system's rocky debris field marks the boundary where planetary formation stalled, a Magnetar's fractured crust exists in a perpetual state of arrested destruction. The quakes shatter surface material into fragments, some mountain-sized, others no larger than pebbles, all suspended above the star by magnetic forces too strong to let them fall. This magnetospheric debris field acts like a cosmic minefield, with crustal shards occasionally colliding or being hurled outward in violent ejections. Unlike our static asteroid belt, though, this one is constantly regenerated by new quakes, creating a self-sustaining cycle of destruction and renewal. What makes these events universal isn't just their raw power, it's their reach. The 2004 flare temporarily ionized Earth's upper atmosphere from 50,000 light-years away, disrupting radio communications and satellite operations. Had it occurred within 20 light-years, it might have stripped our ozone layer entirely. Yet paradoxically, these cataclysms also seed the universe with heavy elements and high-energy particles that might be essential for complex chemistry elsewhere. The same forces that could sterilize planets also create the ingredients for new ones, a reminder that in the cosmos, creation and destruction are often two sides of the same coin. Modern observatories now scan for these extreme events like celestial storm chasers, knowing each one peels back another layer of mystery about matter under conditions we can't replicate on Earth. The Magnetar's roar in 2004 wasn't just a spectacular light show. It was a telegram from nature's most extreme laboratory, written in gamma rays and signed with a cosmic sledgehammer. While some neutron stars scream their presence across the cosmos with blazing pulses of radiation, others communicate through subtler means, ripples in space-time itself. These cosmic whispers come from deformed or rapidly spinning neutron stars emitting continuous gravitational waves, a phenomenon that bends the fabric of reality with every rotation. Unlike the violent chirps detected when neutron stars collide, these signals are persistent and faint, like the hum of a distant engine reverberating through the universe's structure. Take a neutron star with even the tiniest imperfection, a mountain, just centimeters tall, or an asymmetric magnetic field warping its shape. As it spins, this minuscule deformity creates a gravitational wave pattern, a rhythmic pulsing that carries energy away from the star almost imperceptibly. The effect is like a spinning top with a slight wobble, except instead of air resistance, it's space-time itself resisting the distortion. Over millennia, this energy loss slows the star's rotation, turning it into one of nature's most precise braking systems. Detecting these whispers is one of the next great challenges for observatories like LIGO and Virgo. While current instruments are tuned to catch the explosive mergers of black holes and neutron stars, future upgrades aim to listen for these continuous signals, a far trickier task. It's like trying to hear a single violin playing in a hurricane, but if successful, the payoff would be immense. Unlike merger events that last seconds, continuous waves could be monitored for years, offering an unprecedented look into neutron star interiors. The vibrations encoded in these waves could reveal whether the core contains exotic particles like free quarks or hyperons, or if it's a uniform sea of superfluid neutrons. Some of the most promising candidates for detection are accreting neutron stars in binary systems. As these stellar vampires siphon gas from their companions, the infalling matter can create asymmetrical hotspots on their surfaces. The uneven distribution of mass, combined with rapid rotation, makes them ideal gravitational wave factories. Systems like Scorpius X1, a bright X-ray binary, are prime targets for future observations, their whispers potentially carrying clues about how matter behaves at densities unreachable in any lab. What makes these quiet signals so revolutionary is their persistence. A single merger event gives us a snapshot, but continuous waves offer a real-time monitor of neutron star dynamics. A detected signal could track crustal rearrangements after a starquake, measure magnetic field evolution, or even reveal the presence of unseen dark matter particles accumulating in the star's core. The data would be so rich that scientists compare it to switching from black and white photos to full-color video in gravitational wave astronomy. The hunt for these whispers isn't just about adding another detection to the tally. It's about opening a new window into the hidden lives of neutron stars. Every faint ripple carries the potential to answer questions that have puzzled physicists for decades, from the true nature of ultra-dense matter to the limits of magnetic field strength. And when LIGO next-generation detectors finally catch that elusive hum, it won't just be another discovery, it'll be the start of an entirely new conversation with the universe's most extreme objects. At the very heart of a neutron star, where pressures exceed anything recreatable in human laboratories, matter might undergo its most radical transformation, yet dissolving into a primordial soup of free quarks and gluons. This hypothetical state, known as quark-gluon plasma, is thought to exist fleetingly in particle colliders on Earth, but inside neutron star cores, it could persist for millennia, locked under gravitational pressures so intense they overcome the very forces that usually bind quarks together. Imagine crushing an atomic nucleus until its protons and neutrons surrender their identities, their constituent quarks spilling out like beads from a shattered necklace. Under normal conditions, quarks are forever confined within particles by the strong nuclear force, a cosmic rule so absolute it's called color confinement. But in a neutron star's core, densities may reach 10 times that of ordinary atomic nuclei, overwhelming this force and creating a zone where quarks flow freely. This isn't just dense matter, it's matter stripped to its most fundamental building blocks, a state last seen ubiquitously in the universe microseconds after the Big Bang. Some theories take this even further, proposing the existence of strange stars, neutron stars whose quark-gluon cores have absorbed enough energy to produce strange quarks, a heavier flavor normally absent from everyday matter. These exotic objects would effectively be giant hadrons, their entire mass converted into a single, city-sized particle governed by quantum rules we've barely glimpsed in experiments. The implications are staggering. Strange stars might be even denser than neutron stars, their surfaces sharp enough to pierce space-time itself into quantum foam-like structures. Hints of these quark cores come from tantalizing astrophysical clues. Certain neutron stars, like the remarkably massive PSR J0740+6620, exhibit radii smaller than models predict exactly what you'd expect if their interiors collapsed into quark matter. Others cool suspiciously fast, as if their cores were conducting heat with the efficiency of a superfluid quark bath. Even gravitational wave signals from colliding neutron stars sometimes show oscillations suggesting a soft equation of state, consistent with a squishy quark interior rather than a rigid neutron lattice. The smoking gun might lie in sudden stellar transformations. If quark matter is energetically favorable under extreme conditions, a neutron star's core could suddenly melt into this state, triggering a violent rearrangement observable as a giant flare or spin-up event. Some researchers speculate that Magnetar outbursts or fast radio bursts could be signatures of such phase transitions, where cubic kilometers of neutron matter liquefy into quark soup in nanoseconds, releasing enough energy to shake the entire star. Yet quark cores remain one of astrophysics' great unsolved puzzles. Experiments at CERN and Brookhaven can produce quark-gluon plasma, but only in volumes smaller than an atom and for fractions of a second. Neutron stars, by contrast, might harbor this exotic matter in quantities larger than Mount Everest, preserved for epochs. If confirmed, these cosmic laboratories would offer something no collider can: a window into how quarks behave when freed, not just for moments, but for millennia, under conditions so extreme they redefine the word dense. The search continues with every new neutron star discovery, every gravitational wave detection, and every advance in quantum chromodynamics. Whether quark cores or strange stars exist remains unknown, but the very possibility stretches our understanding of matter itself, reminding us that the universe's most familiar substances, protons, neutrons, even atoms, are just temporary arrangements in an ever-shifting quantum landscape. In 1967, a young graduate student named Jocelyn Bell noticed something peculiar in her radio telescope data: a repeating pulse arriving every 1.337 seconds with such precise regularity it seemed almost artificial. The signal, captured by the Interplanetary Scintillation Array in Cambridge, was unlike anything astronomers had seen before. So unnervingly consistent were its beats that Bell and her advisor Anthony Hewish jokingly labeled it LGM1, short for Little Green Men. For a brief, thrilling moment, the team entertained the possibility they might have stumbled upon evidence of extraterrestrial intelligence. The truth turned out to be nearly as extraordinary. What Bell had discovered wasn't an alien broadcast, but the first known pulsar, a rapidly spinning neutron star beaming radiation across space like a cosmic lighthouse. Later identified as PSRB 1919+21, this stellar remnant was the dense core of a long-dead star, packing more mass than our Sun into a sphere barely 20 kilometers wide while spinning faster than a kitchen blender. Its radio pulses, generated by beams of radiation sweeping past Earth with each rotation, were the universe's way of revealing a phenomenon theorists had predicted but never observed: neutron stars in their most dynamic form. The discovery shattered assumptions overnight. Before LGM1, many scientists dismissed neutron stars as theoretical curiosities, too extreme to exist in nature. Yet here was proof that not only did they exist, but they could also act as celestial timekeepers of unparalleled precision. The implications rippled through astrophysics, offering new tools to test Einstein's theories, map the galaxy's magnetic fields, and even hunt for gravitational waves. Pulsars became cosmic laboratories, their clockwork pulses revealing the behavior of matter under conditions impossible to replicate on Earth. Bell's role in this breakthrough, however, was initially overshadowed. When the Nobel Prize in Physics was awarded for the discovery in 1974, it went to Hewish and another radio astronomer, not Bell. The omission sparked lasting debate about scientific recognition, though Bell herself remained gracious, using her platform to advocate for women in STEM. Today, her pulsar is celebrated as a landmark in astronomy, not just for what it revealed about the universe, but for how it reshaped our understanding of what's possible. Those rhythmic pulses, once mistaken for aliens, turned out to be something equally profound: the heartbeat of a stellar corpse, ticking with metronomic precision across the light years. The legacy of LGM1 endures in every pulsar study since. Modern telescopes have catalogued thousands of these spinning relics, each one a testament to the universe's capacity for both violence and precision. Some pulse hundreds of times per second, others flicker erratically, and a precious few, like the original, maintain a regularity that still tempts us to imagine intelligence behind the signal. But the real marvel isn't in the mystery. It's in how an accidental discovery from a 24-year-old student opened a window into the most extreme physics the cosmos has to offer. What began as a curious blip in a data printout became the key to unlocking the secrets of dead stars, and the reminder that sometimes the universe's greatest gifts come dressed as enigmas. While some neutron stars go out in spectacular supernova or collisions, others meet a far quieter fate, fading into cosmic obscurity as their once mighty spins and magnetic fields gradually wither away. This slow demise, known as spin death, occurs when a neutron star's rotational energy bleeds away over millions or billions of years, its pulses growing fainter until they vanish entirely from our detectors. Unlike the dramatic collapse into a black hole, where a star crosses a catastrophic threshold in seconds, this is the universe's version of a dimmer switch being turned down one imperceptible notch at a time. Take the case of an isolated pulsar, born spinning hundreds of times per second. Each rotation emits beams of radiation that act like a cosmic brake, sapping its angular momentum. The stronger the magnetic field, the faster this braking occurs. Some magnetars decelerate so rapidly they lose half their spin speed in just 10,000 years. Over millennia, what began as a brilliant celestial strobe light becomes a sluggish rotator, its pulses arriving seconds or even minutes apart. Eventually, the energy output drops below the threshold needed to generate detectable beams, and the star vanishes from radio telescopes, becoming what astronomers call a radio-quiet neutron star. The journey doesn't end there. Without the particle acceleration fueled by rapid rotation, the star's magnetic field, the engine behind its emissions, begins to decay. Protons in the superfluid core, which once sustained the field through quantum currents, gradually leak away or annihilate. Like a battery losing charge, the field weakens until it can no longer power the spectacular flares or particle winds of its youth. What remains is a cooling ember, visible only as a faint X-ray source radiating residual heat from its million-degree surface. Even this glow fades over time as thermal energy escapes into space, leaving behind a cold, dark sphere of ultra-dense matter, a ghost of stellar grandeur. Contrast this with the violent transition to a black hole. When a neutron star gains too much mass, whether by collision or slowly siphoning matter from a companion, it crosses the Tolman-Oppenheimer-Volkoff limit. In milliseconds, the core succumbs to gravity's inexorable pull, crushing through neutron degeneracy pressure and collapsing beyond spacetime's point of no return. The transformation unleashes gravitational waves and sometimes a kilonova, lighting up detectors across the galaxy. No such fanfare accompanies a spinning neutron star's quiet fade, just the slow, inevitable surrender to entropy. Yet these dark remnants aren't entirely lost to science. Some may reveal themselves through subtle gravitational lensing or rare encounters with interstellar gas clouds, where even a cold neutron star's gravity can ignite brief flares. Others might be discovered orbiting stars, their presence betrayed by slight wobbles in their companion's motion. And in the distant future, when the universe has cooled nearly to absolute zero, these silent sentinels may be the last macroscopic objects remaining, their protons decaying at last, marking the final chapter in the story of stellar corpses. The quiet death of a neutron star is a reminder that not all cosmic endings are fireworks. Some are whispers fading into the background hum of the universe, their legacy written not in light but in the stubborn persistence of matter pushed to its absolute limits. Imagine a celestial object so massive it could outweigh the sun, yet compact enough to fit inside your morning commute. The average neutron star spans just 20 kilometers across, a diameter so modest you could drive from one end to the other in under 20 minutes on Earth. To grasp how absurdly dense that is, picture overlaying one onto Manhattan Island. Its entire structure would barely stretch from Battery Park to Harlem, yet it would contain the mass of 500,000 Earths squeezed into that tiny footprint. There's a brutal elegance to this compactness. Neutron stars represent the universe's ultimate game of gravitational Jenga. Any larger, and they'd collapse into black holes. Any smaller, and they couldn't sustain the crushing pressure needed to survive. The size limit stems from a delicate balance between two opposing forces: neutron degeneracy pressure, the quantum rule that prevents neutrons from occupying the same space, and gravity's relentless squeeze. Add more mass and gravity wins, compressing the star further until it crosses the threshold into black hole territory. But here's what's truly wild: that 20-kilometer span isn't uniform. The star's crust, a crystalline lattice of iron nuclei, might be just a kilometer thick, like the brittle shell of an egg protecting the liquid chaos beneath. Deeper in, the neutrons themselves start behaving like a frictionless superfluid, flowing without viscosity in a quantum dance. By the time you reach the core, matter may have shed all pretenses of normality, dissolving into free quarks or exotic particles that defy known physics. This minuscule scale has cosmic consequences. A neutron star's compactness is why its surface gravity can be 100 billion times Earth's. Light emitted just above its surface loses significant energy climbing away, a phenomenon called gravitational redshift. It's also why their spins can reach ludicrous speeds without flying apart. The equator of a millisecond pulsar might move at a quarter the speed of light, yet the star's immense gravity keeps every atom welded in place. Compare this to white dwarfs, another type of stellar corpse which might be Earth-sized but contain only half a sun's mass. The difference, electron degeneracy pressure, holds them up, a far weaker force than what keeps neutron stars intact. It's the cosmic equivalent of comparing a balloon to a diamond. One is dense by everyday standards, the other redefines density altogether. Yet even neutron stars have their limits. The smallest observed, Pulsar J0453 plus 1559, is estimated at just 12 kilometers across, pushing the lower boundary of how small such an object can be before its own neutrons rebel against compression. These dimensions aren't arbitrary. They're nature's way of enforcing the rules of quantum mechanics on a cosmic scale, proving that when it comes to the universe's most extreme objects, size isn't just a measurement, it's a matter of survival. While most pulsars announce their presence with rhythmic radio waves, some choose a far more energetic language, blinking in X-rays so intense they'd pierce through solid lead. Take Hercules X1, an X-ray pulsar discovered in 1971, whose beams carry millions of times more energy than your typical radio pulsar. Here's the twist: unlike rotation-powered pulsars that gradually slow as they radiate energy, objects like Hercules X1 are fueled by cosmic theft, siphoning gas from a companion star at such ferocious rates that the infalling matter erupts in X-ray flashes hot enough to vaporize planets. The physics behind these accretion-powered pulses reads like a stellar heist novel. As gas spirals from Hercules X1's companion star, a blue giant called HC Hercules, it doesn't fall directly onto the neutron star. Instead, it gets funneled by magnetic fields 1 trillion times stronger than Earth's, channeled toward the magnetic poles like water down a cosmic drain. When this superheated plasma smashes into the star's surface at half the speed of light, it creates searing hotspots that blaze in X-rays. Each rotation sweeps these beams past Earth like a lighthouse powered by thermonuclear fire, pulsing every 24 seconds with clockwork precision. What makes X-ray pulsars fundamentally different isn't just their energy, it's their lifeline. Rotation-powered pulsars are essentially stellar batteries, slowly discharging the energy of their spin. But accretion-powered systems like Hercules X1 are cosmic generators, converting stolen mass into fresh radiation. The more gas they steal, the brighter they shine. Some even flicker irregularly as clumps of matter crash down in unpredictable avalanches. This creates a paradox. While they're far more luminous than radio pulsars, their spin rates stay remarkably stable, governed by the delicate balance between accretion torque and magnetic braking. Hercules X1 itself is a study in extremes. Its companion star isn't just donating gas, it's being warped into a teardrop shape by the neutron star's gravity, with one side perpetually scorched by X-ray irradiation. Every 7 days, the pulsar dips behind this distorted star, causing X-ray eclipses that let astronomers map the system's geometry with astonishing precision. Even weirder, the pulsar exhibits superorbital cycles every 35 days, likely due to a wobbling accretion disk that periodically blocks our view like a slow-motion shutter. The discovery of X-ray pulsars revolutionized our understanding of neutron star diversity. Before Hercules X1, pulsars were seen as isolated, radio-emitting metronomes. Now we know they're shape-shifters capable of switching between states as their environments change. Some, like Sen X3, even transition between X-ray and radio pulsations depending on how greedily they feed. These systems prove neutron stars aren't one-trick ponies but cosmic chameleons, adapting their signals to the violent physics of their surroundings. Detecting their high-energy pulses requires space telescopes like NAS and NICER, which reads X-ray fluctuations with microsecond timing. What they've revealed is a hidden population of neutron stars too busy devouring their neighbors to bother with radio signal stellar vampires whose frantic meals illuminate the universe in bursts of radiation visible across galactic distances. So while radio pulsars might be the universe's timekeepers, X-ray pulsars are its flashy entertainers putting on light shows where the stage is a magnetic prison. The actors are streams of superheated plasma, and the ticket price is the slow annihilation of a companion star. If you've ever wondered why pulsars flash like cosmic lighthouses, the answer lies in a celestial quirk of geometry. Their spin axis and magnetic axis aren't aligned. Picture a spinning top with a flashlight glued to its side at a crooked angle. Every time the top rotates, the flashlight beam sweeps past your eyes, creating a pulse of light. That's essentially how a pulsar works, except instead of a toy, it's a city-sized neutron star with magnetic fields strong enough to rip atoms apart. And instead of a flashlight, it's hurling focused beams of radiation across the galaxy. The misalignment is what makes these stellar remnants visible to us at all. A perfectly aligned neutron star, one where its magnetic poles point directly along its rotation axis, would blast energy uniformly in all directions like a dim, omnidirectional bulb. But nature prefers chaos. When a neutron star forms in a supernova's violent collapse, the magnetic field, which was once buried deep in the progenitor star's interior, gets scrambled. The result, a tilt between the star's rotation axis and its magnetic axis, often by 10 to 45 degrees. This offset forces the radiation emitted from the magnetic poles, typically radio waves, X-rays or gamma rays, to shoot out in narrow cones, sweeping through space like the beam of a searchlight. Here's where the magic happens. If Earth happens to lie in the path of one of those sweeping cones, we detect a pulse every time the beam crosses our line of sight. This is why some pulsars appear to blink with such perfect regularity. Their rotation carries the radiation beam past us like clockwork. The Crab pulsar, for instance, spins 30 times per second, and with each rotation, its misaligned magnetic beams sweep past Earth, creating 30 pulses per second that arrive with precision rivaling atomic clocks. But not all pulsars flash so neatly. Some, like the Vela pulsar, exhibit interpulses, secondary flashes suggesting their magnetic axes are nearly perpendicular to their spin axes, creating a double lighthouse effect. Others, known as nulling pulsars, occasionally skip beats when their beam geometry temporarily misses Earth, like a flickering bulb in a cosmic storm. These variations aren't just quirks, they're clues. By studying the timing and shape of pulses, astronomers can map a neutron star's magnetic field structure, infer its tilt angle, and even detect wobbles in its spin called precession, where the rotation axis itself slowly circles like a wobbly top. The misalignment also explains why some neutron stars evolve into different types of pulsars over time. As a pulsar ages, its magnetic field weakens, and the angle between its spin and magnetic axes may drift toward alignment. This could turn a once bright radio pulsar into a quieter, nearly invisible object unless it's resurrected by stealing matter from a companion star, which can re-excite the magnetic field and re-tilt the axes, restarting the pulsar's lighthouse effect. So while a perfectly aligned neutron star might seem like the simpler, more orderly outcome, It's the universe's love of asymmetry that gives us these brilliant cosmic beacons. Without that critical tilt, pulsars would vanish into the darkness, their rhythmic pulses silent, and we'd lose one of astronomy's most powerful tools for probing the extremes of gravity, matter, and space-time itself. The next time you see an artist's illustration of a pulsar's twin beams spiraling through space, remember, it's not just artistic flair. It's the signature of a star that refused to spin straight, and in doing so, lit up the universe. Neutron stars aren't just uniform spheres of scorching heat. Their surfaces can blaze with searing hotspots, localized infernos where temperatures skyrocket to tens of millions of degrees. These patches of extreme brightness often cluster around magnetic poles, where the star's unimaginably strong magnetic fields funnel charged particles into violent collisions, creating X-ray flares so intense they outshine the rest of the star's surface combined. Picture a welder's torch focused into a pinpoint on an icy lake, except the torch is powered by physics that defy earthly logic, and the lake is a crust of iron nuclei packed tighter than diamonds. These hotspots don't just glow, they sculpt the very pulses we detect from Earth. As the neutron star spins, the hotspots whip around like cosmic strobe lights, their radiation sweeping across our line of sight in predictable rhythms. The shape of those pulses, whether sharp peaks or broad waves, holds secrets about the hotspot size, temperature, and even their geography. Some pulsars, like Geminga, show double-peaked pulses suggesting twin hotspots on opposite hemispheres, while others flicker erratically, hinting at unstable magnetic fields shredding and reforming these fiery patches in real time. Mapping these regions isn't just academic curiosity, it's a window into the star's hidden dynamics. NASA's NICER telescope, designed to study neutron star surfaces, has captured temperature maps of pulsars like Pulsar J0030 plus 0451, revealing hotspots that defy expectations. Instead of symmetrical poles, some stars sport lopsided clusters of hotspots, suggesting magnetic fields twisted into bizarre configurations during the star's violent birth. Others, like the Black Widow pulsar, show migrating hotspots that drift across the surface as the star's magnetic crust fractures under strain, like tectonic plates sliding over a molten core. The heat itself is generated by particle bombardment so relentless it could power civilizations. Electrons, accelerated to near light speed along magnetic field lines, slam into the star's surface with enough force to trigger inverse Compton scattering, a process that converts kinetic energy into X-rays. In Magnetars, these hotspots can temporarily outshine the entire Milky Way, their radiation so focused it could sterilize a planet light years away. Yet despite their fury, these patches are tiny, some no larger than a football field on a star just 20 kilometers wide, a testament to how precisely the universe concentrates its most extreme energies. What's truly surprising is how these hotspots challenge our assumptions. Traditional models predicted neat, circular polar caps, but real-world observations revealed jagged, irregular shapes, some elongated by stellar rotation, others split into arc-like fragments by magnetic turbulence. This isn't just surface decoration, it's evidence of a neutron star's internal chaos leaking outward, where magnetic fields a quadrillion times stronger than Earth sculpt plasma into structures we're only beginning to understand. So the next time you hear about a pulsar's steady beat, remember, it's not just a metronome in the dark. Each pulse is a flaming fingerprint, a signpost of violence and order coexisting on the most unforgiving surfaces in the universe. And as telescopes grow sharper, these hotspots will keep whispering secrets about magnetic monsters, stellar rebirth, and the strange physics that govern the cosmos' most volatile survivors. Rippling across billions of light years, the faint whispers from the universe's most distant neutron stars aren't just signals, they're portals to the cosmic past. When we detect a neutron star 13 billion light years away, we're not seeing it as it exists today. but as it appeared when the universe was a mere 800 million years old, a stellar newborn blinking in the primordial darkness. This isn't just astronomy, it's time travel, with each photon carrying a snapshot of conditions during an era when galaxies were just assembling their first stars, and the cosmos was still laced with the leftover heat of the Big Bang. Take PSOJ 03 2.5-1823, a pulsar whose light spent 12.8 billion years journeying to reach us. The vibrations in its pulses encode information about the interstellar medium it traversed, gas that hadn't yet been enriched with heavy elements like iron or gold, preserving a chemical fossil record of the universe's infancy. Unlike nearby neutron stars that reveal contemporary physics, these ancient beacons expose how gravitational waves behaved when spacetime was less stretched, how magnetic fields operated before galactic dynamos fully formed, and how matter collapsed under conditions far denser than anything in today's universe. The implications for cosmic evolution studies are staggering. By comparing these relic neutron stars to their modern counterparts, astronomers have uncovered something unexpected. The earliest ones spin slower and have weaker magnetic fields than contemporary pulsars. This suggests the first neutron stars formed differently, perhaps from faster rotating progenitor stars in environments rich with dark matter. Some theories even propose that primordial neutron stars acted as seeds for the universe's first supermassive black holes, their rapid growth fueled by the dense gas of the early cosmos before star formation became orderly. What makes these distant time capsules truly indispensable is their role in mapping the universe's expansion history. As their light journeys through space, it gets stretched by the fabric of an expanding cosmos, an effect called redshift. The degree of stretching reveals how fast the universe was growing at different epochs, helping astronomers calibrate dark energy's influence with precision. Some neutron stars observed at extreme distances exhibit redshift values so high their pulses arrive flattened into near-infrared waves, their original radio frequencies lost to cosmic expansion. Yet the greatest revelation might be what these ancient pulsars lack. Their emission patterns show no traces of certain heavy elements, confirming they formed before the universe's first generations of stars had time to forge and scatter metals through supernova. It's like finding a cave painting untouched by later civilizations, a pure relic of the cosmos' wild youth. As newer telescopes like the Square Kilometer Array come online, their unprecedented sensitivity may soon uncover neutron stars from the universe's first 500 million years, probing an era when the very laws of physics might have operated under different constants. Peering at these distant specks, we're not just studying stars, we're witnessing the universe's childhood through the lens of its most extreme objects. Each pulse is a timestamp from an epoch when galaxies were embryonic, dark matter ruled supreme, and the foundations for everything we see today were being laid in violence and light. The most astonishing part, we've only just begun decoding their messages. The next generation of observatories might find neutron stars so ancient they challenge our understanding of when the first stars could even form, rewriting cosmic history with every flicker from the abyss of time. At the heart of the Crab Nebula, a cosmic masterpiece stretching 12 light-years across, lies an engine of unimaginable power, the Crab Pulsar. This neutron star, spinning 30 times per second, doesn't just sit quietly in the wreckage of its ancient supernova. It pumps energy into the surrounding nebula like a celestial dynamo, illuminating filaments of gas with the brilliance of 75,000 suns. The spectacle isn't just pretty, it's physics at its most extreme, where the raw power of a stellar corpse transforms chaos into light. Picture this pulsar's influence like a turbine in a cosmic power plant. Its rapidly rotating magnetic field, trillions of times stronger than Earth's, accelerates electrons to nearly light speed, creating a whirlwind of high-energy particles. These charged particles then spiral along magnetic field lines, emitting synchrotron radiation. a frenetic dance that glows across the electromagnetic spectrum from radio waves to gamma rays. The result, a nebula that doesn't just passively glow from leftover supernova heat, but actively shines with energy siphoned directly from the pulsar's spin. The numbers behind this process defy comprehension. The Crab pulsar loses energy at a rate of about 5 million times the Sun's total output, all just to keep its nebula illuminated. That energy doesn't vanish, it transfers to the surrounding gas, exciting atoms and molecules until they fluoresce like a neon sign on galactic scales. The most visible tendrils, captured in Hubble's iconic images, trace where this particle wind collides with slower-moving debris from the original explosion, creating shock waves that ripple through space at 500 kilometers per second. This isn't just a one-way street. The nebula itself acts as a brake on the pulsar, its resistance gradually slowing the star's rotation by milliseconds per century. It's a feedback loop written in physics. The pulsar energizes the nebula saps the pulsar's spin, and together they evolve in a slow cosmic waltz. Spectroscopic studies reveal the nebula's chemistry changing in real time, enriched by heavy elements forged in the supernova and now stirred by the pulsar's relentless particle wind. The Crab's brilliance isn't unique, just exceptionally vivid. Other pulsar-powered nebulae like Vela or G21.5-0.9 showcase similar dynamics on quieter scales. But what makes the Crab Nebula extraordinary is its youth. At just 970 years old as of 2024, it's a stellar infant compared to most supernova remnants, offering astronomers a front-row seat to watch a pulsar reshape its surroundings in human timescales. The filaments expand visibly year by year, while the pulsar's precise flashes let researchers track even minuscule changes in its spin-down rate. Hidden in this interplay is a revelation about cosmic recycling. The same processes that light up the Crab Nebula also seed it with the ingredients for future stars and planets. The pulsar's particle wind carries not just energy, but also freshly synthesized elements: carbon, oxygen, even gold, scattering them into interstellar space. Over millennia, these atoms will mix with galactic gas clouds, eventually collapsing into new solar systems. The glow we admire today is more than a light show. It's the universe's way of forging tomorrow's worlds from yesterday's catastrophe. So when you gaze at images of the Crab Nebula's swirling colors, remember, you're not just seeing debris, you're witnessing a conversation between a dead star and its legacy, written in particle winds and magnetic fields, a testament to how the most violent ends can ignite the most enduring light. Even the most ravenous cosmic eaters sometimes have messy table manners. Take Vela X1, a neutron star locked in a deadly dance with a blue supergiant companion, greedily siphoning gas from its neighbor's stellar winds until suddenly it doesn't. Every few hundred orbits, this X-ray pulsar does something bizarre. It burps. Violent hiccups in its accretion flow cause its normally steady X-ray emissions to plummet, as if some unseen cosmic hand flicked a dimmer switch halfway across the galaxy. These aren't minor fluctuations, they're full-blown digestive rebellions. For hours or even days, Vela X1's X-ray output drops by 90% or more, leaving astronomers puzzled. The leading theory: the star's messy eating habits create a buildup of material in its accretion disk, like water backing up behind a clogged drain. Eventually, the pressure becomes too much, and the system belches out a chaotic plume of gas and magnetic turbulence. This expulsion temporarily blocks our view of the hot inner disk, casting the pulsar into sudden shadow. What's fascinating is how these hiccups reveal the delicate balance of power in such systems. Normally, the neutron star's gravity and magnetic fields neatly funnel stolen gas onto its poles at near light speeds. But when too much material floods in at once, perhaps due to clumps in the donor star's wind, the magnetic gates get overwhelmed. The result is a cosmic traffic jam where charged particles back up, collide, and eventually erupt outward in a magnetically driven belch. Some observations even suggest these events launch relativistic jets perpendicular to the disk, like champagne corks popping from an overpressurized bottle. The aftermath is just as intriguing. Post-hiccup, Vela X1 doesn't immediately return to normal. It flickers back to life like a sputtering engine, its X-rays ramping up unevenly as the accretion flow stabilizes. This recovery phase lets astronomers map the pulsar's magnetic geography in ways normally impossible, each flicker tracing how the star's field lines reconnect and reorganize after the disruption. Similar behavior has been spotted in other X-ray binaries like Sen X3 and Hercules X1, suggesting this isn't just Vela X1's quirk, it's a fundamental feature of how neutron stars binge-eat in turbulent stellar environments. The burps might even serve a regulatory purpose, preventing the pulsar from gorging itself into a dangerous mass buildup that could trigger a collapse into a black hole. So while these events might seem like cosmic indigestion, they're actually vital diagnostics, violent reminders that even the universe's most extreme dynamos have limits. Every hiccup encodes secrets about magnetic field strengths, plasma physics, and the chaotic dynamics of stolen matter on the brink of oblivion. When a neutron star is born in the chaos of a supernova, it doesn't just inherit a dead star's mass, it inherits its fury. Some of these stellar remnants get kicked away with such unimaginable force they don't just escape their birthplaces, they're flung completely out of their home galaxies, destined to drift forever in the empty vastness between galaxies. These cosmic outcasts, known as hypervelocity neutron stars, are among the universe's loneliest objects, racing through the abyss at speeds exceeding 2 million miles per hour, too fast for any galaxy's gravity to reclaim them. Take RxJ0822-4300, a neutron star hurtling through the Puppis constellation at roughly 3 million miles per hour. Traced back to a supernova remnant roughly 7,000 light-years away, this rogue traveler shows no signs of slowing, its trajectory pointing unmistakably toward intergalactic space. At its current speed, it could cross the entire Milky Way in just 25 million years, a cosmic blink, before breaking free entirely. What kind of explosion could launch a city-sized object with such violence? The answer lies in asymmetrical supernova, where the collapsing star's detonation isn't uniform. If more material blasts outward in one direction, the newborn neutron star rockets in the opposite direction like a cannon recoiling, conserving the explosion's momentum in a single, catastrophic shove. The physics behind these kicks is staggering. During collapse, if even 1% more neutrinos or ejected matter streams out along one axis, the resulting imbalance can accelerate the neutron star to thousands of kilometers per second. It's nature's version of a slingshot, where the star's own death throes become its propulsion. Some models suggest magnetic fields play a role too. If the dying star's magnetic axis tilts off-center, the resulting torque might add extra thrust like a poorly aligned rocket engine. But the true marvel is where these exiles end up. Unlike stars bound to galaxies, hypervelocity neutron stars face an eternity of isolation. With no interstellar gas to slow them down and no celestial neighbors for company, they'll drift through near-perfect vacuum until their pulses fade into silence. Yet, even in this emptiness, they might leave traces. A neutron star moving at relativistic speeds through sparse intergalactic gas could generate shock waves visible in X-rays, a faint wake marking its passage like a ship's prow cutting through calm waters. The discovery of candidates like RxJ0822-4300 raises tantalizing questions. How many more of these galactic fugitives exist, unseen because their beams don't intersect Earth? Could some intergalactic neutron stars be ancient refugees from galaxies long since absorbed by the Milky Way? Their trajectories, if we could trace them backward, might reveal forgotten collisions or bursts of star formation from epochs when our galaxy looked entirely different. These runaway stars are more than just cosmic curiosities, they're extreme tests of astrophysical models. Their velocities challenge our understanding of supernova mechanics, forcing theorists to refine simulations of stellar deaths. And if, as some suspect, a population of neutron stars exists entirely beyond galaxies, they could be the universe's hidden messengers, silent travelers carrying secrets from the emptiest places imaginable. Even the most rigid neutron star isn't completely immune to cosmic influences, especially when a close companion star starts playing gravitational tug-of-war. While these stellar corpses are often imagined as perfect spheres of ultra-dense matter, the reality is far more dynamic. When locked in tight orbits with other massive objects, neutron stars experience tidal forces powerful enough to induce subtle deformations, stretching and squashing their structure by millimeters in a cosmic dance of gravity and resistance. These tidal distortions work differently than ocean tides on Earth. Our planet's tidal bulges arise because liquid water easily shifts under the moon's pull, while the solid crust barely moves. But on a neutron star, the entire structure from its ironclad crust to its hypothesized quark gluon core gets warped. The star's ridiculous density makes it resist deformation fiercely, so even a nearby companion weighing several suns might only raise tides a few centimeters high. Yet that tiny bulge, constantly shifting as the star's orbit, has cosmic consequences. It radiates gravitational waves, those faint ripples in spacetime predicted by Einstein. The physics behind this is mesmerizing. As tidal forces massage the neutron star, they transfer orbital energy into heat through internal friction. Imagine squeezing a stress ball over and over until it warms in your hand. This process, called tidal heating, can actually slow the star's orbital decay, subtly altering their in-spiral trajectories. Some binary systems, like the famous Hulse-Taylor pulsar, show orbital changes that match these predictions with jaw-dropping precision, proving neutron stars aren't just passive participants in their gravitational tangos. What's wild is how these tides connect to gravitational wave astronomy. When LIGO detects merging neutron stars, the final moments before collision reveal tidal distortions through subtle waveform changes, like listening to a bell's tone shift as it's dented. The degree of deformation clues scientists into the star's internal structure. A softer, more deformable core suggests exotic quark matter, while stubborn resistance hints at an ultra-rigid neutron lattice. In 2017, GW 170,817 gravitational waves hinted at tides distorting the neutron stars by about a meter, a tiny shift for objects 12 kilometers wide, but enough to rule out certain equations of state for ultra-dense matter. These tidal interactions aren't just academic curiosities, they're cosmic diagnostics. By studying how neutron stars warp under gravitational stress, we're essentially probing their interiors with spacetime itself as our tool. Every millimeter of deformation, every ripple in the gravitational wave signal, carries encrypted messages about what lies beneath those impenetrable surfaces, a secret language of pressure, density, and quantum forces waiting to be decoded by the next generation of observatories. Tucked away in the constellation grooves, an unassuming flicker of radio waves carries an extraordinary message from the early universe. Pulsar J 2144-3933, the oldest known pulsar, has been spinning quietly for nearly 10 billion years. To put that age into perspective, when this stellar remnant first began its steady pulses, the Milky Way was still assembling itself from primordial gas clouds, and Earth wouldn't exist for another 6 billion years. What makes this pulsar truly remarkable isn't just its longevity, but what it reveals about the endurance of cosmic lighthouses long after their fiery births. Unlike the frenetic millisecond pulsars that dominate modern surveys, Pulsar J 2144-3933 rotates leisurely once every 8.5 seconds, a sedate pace that belies its incredible staying power. Most pulsars fade into obscurity within a few tens of millions of years as their magnetic fields decay and their rotations slow to a crawl. Yet this ancient survivor has defied the odds, its faint but persistent signal enduring across epochs when entire galaxies have merged and stars have been born and died. The secret lies in its unusually weak magnetic field, about 1,000 times less intense than typical pulsars. This muted magnetism means it bleeds rotational energy at a glacial pace, like a wind-up toy designed to outlast civilizations. But the implications stretch far beyond one old neutron star. Pulsar J 2144-3933 challenges our assumptions about stellar life cycles. Its existence suggests that the first generations of massive stars, those that died to create such pulsars, may have formed differently than today's stellar giants. Perhaps they collapsed more symmetrically, imparting gentler natal kicks that left their remnants with slower spins and quieter magnetic personalities. Or maybe the early universe's lower metal content allowed their progenitors to shed mass more efficiently, resulting in neutron stars primed for marathon lifetimes rather than brilliant, short-lived displays. This pulsar also serves as a cosmic counterweight to the dazzling but ephemeral phenomena we often prioritize. While gamma-ray bursts and magnetar flares dominate headlines, Pulsar J 2144-3933 represents the universe's quiet majority neutron stars that fade into the background, pulsing steadfastly through cosmic time. Its radio whispers, though faint, carry encoded details about the interstellar medium's evolution, the gravitational wave background, and even the stability of fundamental constants over billion-year spans. Yet the greatest mystery remains how we detected it at all. Most pulsar surveys are tuned to catch rapid, millisecond pulses, making this slow, elderly outlier a lucky find. Its discovery hints at a vast hidden population of similarly ancient neutron stars, their languid spins and dim emissions eluding our telescopes. If even a fraction of the first stellar generations left behind such enduring remnants, the cosmos could be thrumming with their subtle rhythms, a ghostly chorus of the universe's earliest explosions, still ticking like forgotten clocks in the dark. The Milky Way likely teems with over 100 million neutron stars, stellar remnants lurking in the darkness of our galaxy like cosmic ghosts. Yet despite their staggering numbers, we've detected fewer than 3,000. Why the disconnect? Imagine trying to spot a lone lighthouse keeper's lantern from thousands of miles away, but only when the beam happens to point directly at you. That's essentially the challenge astronomers face when hunting these elusive objects. Neutron stars are masters of invisibility. Unless they're actively pulsing radiation toward Earth, visible only if their beams intersect our line of sight, they're extraordinarily difficult to detect. Isolated neutron stars, those without companion stars to feed on, cool rapidly, fading into near-total darkness except for faint X-ray whispers from their million-degree surfaces. Even the most sensitive telescopes struggle to distinguish these dim embers from background cosmic noise unless they're relatively close within a few hundred light-years. Then there's the interstellar obstacle course. Giant molecular clouds, those stellar nurseries filled with dust and gas, act like cosmic fog, absorbing the very radio and X-ray signals neutron stars emit. A pulsar just a few thousand light-years away might be completely obscured if it's tucked behind one of these thick veils. It's like trying to hear someone whisper through a soundproof wall. The message exists, but the medium gets in the way. But here's the twist. Some of the most revealing discoveries come from what neutron stars don't do. When astronomers track stars moving through space and notice subtle wobbles without visible companions, it often hints at an unseen neutron star's gravitational tug. These dark neutron stars leave fingerprints in the motion of nearby objects, their presence betrayed by the way they warp space-time around them. The famous companion to the star HD 49700 is one such phantom. its existence inferred solely by how it perturbs its visible partner's orbit. The sheer scale of the search adds another layer of complexity. Surveying the entire Milky Way for faint, city-sized objects is like combing every beach on Earth for a single speck of magnetic sand. Even with modern radio telescopes and X-ray observatories, we've barely scratched the surface. The ones we do spot tend to be either exceptionally bright, unusually close, or conveniently angled to flash their beams in our direction. The rest, they're out there, spinning silently in the dark, a hidden population of stellar corpses waiting for the right technology or the right moment to reveal themselves. Yet every new detection reshapes our understanding. Some neutron stars, like the recently discovered PSRJ 0946+1006, defy expectations by pulsing in ways that suggest entirely new subclasses. Others, hidden in plain sight, emerge when archival data gets reanalyzed with sharper algorithms. With next-generation telescopes like the Square Kilometer Array coming online, astronomers anticipate uncovering tens of thousands more, peeling back the galaxy's obscuring layers to reveal a universe far richer in stellar ghosts than we ever imagined. So while 100 million might sound like an overwhelming estimate, it's also a thrilling reminder of how much remains to be discovered. The cosmos isn't just hiding these extreme objects, it's practically daring us to find them one pulse, one wobble, one X-ray flicker at a time. Deep in the cosmos, neutron star PSRB 0329+54 isn't just pulsing, it's singing. This distant stellar remnant produces radio waves that oscillate with such rhythmic precision, they resemble the haunting tones of a cosmic choir. When astronomers first analyzed its signal, they discovered something astonishing. The pulsar's emissions weren't just steady clicks but melodic fluctuations. Played through a speaker, these oscillations sound like an otherworldly hum, drifting between frequencies like a theremin echoing across light years. The secret behind this celestial music lies in the turbulent plasma surrounding the star. As charged particles race along the neutron star's magnetic field lines, they create instabilities, ripples in the flow of ionized gas. Picture blowing across the top of a bottle where the air's vibration produces a musical note. Here, plasma acts like that vibrating air column, with magnetic fields shaping the oscillations into coherent patterns. Certain frequencies resonate more strongly, amplifying specific notes while suppressing others, resulting in a signal that's less random, static, and more structured symphony. What's even more fascinating is how these oscillations evolve. Some pulsars, like PSRB 0834+06, exhibit harmonic overtones, additional frequencies that are mathematical multiples of the main tone, much like the rich harmonics of a plucked guitar string. These patterns suggest the plasma isn't just chaotically sloshing around. It's organizing itself into standing waves, with nodes and antinodes forming in the magnetosphere like sound waves in a pipe organ. The conditions required for this singing are incredibly specific. The plasma must be dense enough to sustain coherent vibrations, yet not so turbulent that it drowns out the signal. The neutron star's magnetic field acts as both conductor and instrument, channeling the particles into resonant structures. Occasionally, these oscillations even modulate the star's regular pulses, creating a secondary rhythm beneath the primary beat, like a drummer adding syncopation to a metronome's steady tick. Astronomers have turned these radio oscillations into audible soundscapes, translating the raw data into frequencies the human ear can perceive. The result: pulsars don't just tick, they warble, chirp, and even whistle, their tones shifting as the plasma environment changes over days or weeks. Some sound eerily like birdsong, while others evoke the deep, resonant hum of a Tibetan singing bowl. These aren't just artistic interpretations, they're direct sonic representations of physics playing out under conditions we can't replicate on Earth. Beyond their eerie beauty, these oscillations are cosmic diagnostics. By studying their frequencies, scientists can map the invisible plasma surrounding the star, inferring its density, temperature, and how it interacts with the magnetic field. Sudden changes in the song might signal starquakes, rearranging the crust or magnetic reconnections, launching plasma storms. In a way, pulsars aren't just dead stars, they're celestial Stradivarius instruments, their melodies composed by the laws of electromagnetism and fluid dynamics, playing a concerto written in the language of the universe itself. When two neutron stars spiral toward collision, they don't just merge, they unleash one of the universe's most catastrophic light shows, short gamma-ray bursts. These explosions, lasting mere milliseconds to 2 seconds, pack more energy than our Sun will emit in its entire 10 billion-year lifetime. The 2017 detection of gravitational wave event GW170817 gave humanity front-row seats to this phenomenon, when neutron stars 300 million light-years away collided in a cataclysm that temporarily outshone every star in the observable universe combined. The physics behind these bursts is almost incomprehensible, as the stars, each 12 kilometers wide but weighing more than our Sun, finally touch. Their cores merge at nearly light speed, creating temperatures exceeding 1 trillion degrees. The impact shreds their neutron-rich material into jets of ultra-relativistic plasma, funneled along magnetic field lines like cosmic fire hoses. These jets, narrower than a pencil's width but stretching billions of kilometers, blast through space at 99.99% light speed. If one happened within 40 light-years of Earth, the radiation would sterilize our planet in seconds. What makes GW170817 so groundbreaking isn't just the burst itself, it's the afterglow. Unlike fleeting gamma-ray flashes that vanish instantly, this event produced a kilonova, an infrared and optical glow powered by radioactive decay of heavy elements forged in the collision. For days, telescopes worldwide watched as the expanding debris cloud radiated with the brilliance of 1 million suns, its light curve matching predictions for rapid neutron capture. This confirmed neutron star mergers as the universe's primary factories for gold, platinum, and uranium. Your wedding ring likely contains atoms birthed in such an explosion billions of years ago. The event also solved a decades-old cosmic mystery. Since the first gamma-ray bursts were detected in the 1960s, astronomers debated their origins. Some were clearly from collapsing massive stars, but the shorter bursts lasting under 2 seconds defied explanation. The 2017 merger proved these brief flashes come from neutron star collisions, their jets pointed fortuitously at Earth like celestial laser beams. Even more astonishing, the burst's energy output varied wildly across wavelengths, suggesting the jets weren't uniform but fragmented like a shotgun blast rather than a single bullet. Yet the true revelation lies in what we didn't see immediately. Hours after the burst, X-ray and radio emissions flared unexpectedly, revealing a structured afterburn caused by the jets interacting with interstellar material. This delayed emission, modeled extensively since the event, suggests colliding neutron stars don't just explode, they leave behind chaotic debris fields where magnetic reconnections and shock waves continue releasing energy for weeks. Some theories even propose these collisions birth highly magnetized neutron stars or low-mass black holes, their nascent energy output powering prolonged electromagnetic fireworks. The legacy of GW170817 endures in every gamma-ray burst study since, by combining gravitational wave data with multi-wavelength observations. Astronomers now hunt these events systematically, each new detection peeling back layers of mystery about how matter behaves at densities unreachable in any lab. These aren't just explosions, they're Rosetta Stones for decoding the universe's most extreme physics, written in light, gravitational ripples, and the very elements that make up our world. And with upgraded detectors coming online, the next neutron star collision might reveal something even more extraordinary. perhaps a burst so bright it redefines what we thought was possible. Deep beneath the searing surface of a neutron star, where pressures crush matter into forms that defy imagination, another transformation unfolds over eons, the slow, inevitable freeze of a stellar corpse. As these ultra-dense remnants cool over millions of years, their cores may undergo a metamorphosis more alien than anything on Earth, the crystallization of nuclear matter into a lattice so dense it makes diamond resemble tissue paper. This isn't just cooling, it's the universe's most extreme form of thermodynamics, where quantum rules rewrite the very definition of a solid. Picture the process like water turning to ice, but with conditions so extreme the comparison barely holds. A neutron star's core begins as a seething ocean of degenerate neutrons, packed tighter than atoms in a neutron star's own crust. As thermal energy gradually leaks away through X-ray emission, temperatures drop from billions to mere millions of degrees, allowing the neutrons to settle into an ordered crystalline structure. The resulting nuclear pasta phase, with its spaghetti-like strands and lasagna-like layers, gives way to something even stranger, a quantum crystal where neutrons align in rigid patterns, yet remain so dense that a teaspoonful would outweigh Mount Everest. What makes this freeze so extraordinary is the scale of forces involved. Earth's core solidifies over billions of years as iron crystallizes under pressures of a few million atmospheres. A neutron star's core endures pressures 100 trillion times greater enough to overcome the Pauli exclusion principle, the quantum law that typically prevents particles from occupying the same state. Here, neutrons surrender to the crush, forming a lattice where vibrations propagate at near light speed, and thermal conductivity rivals that of a perfect superfluid. The evidence for this deep freeze comes from surprising observations. Older neutron stars, like the 10-million-year-old Pulsar J010-8-1431, cool faster than models predict, a sign their interiors might be transitioning to crystalline phases, releasing latent heat as they reorganize. Some exhibit temperature cliffs in their cooling curves, sudden drops consistent with phase changes in their cores. Even gravitational wave signals from colliding neutron stars hint at this rigidity. The way they deform before merging suggests interiors far stiffer than pure neutron fluid. Yet the full picture remains elusive. Simulations suggest the crystallization might start at the core and creep outward, or occur in patches separated by lingering pockets of superfluid. Magnetic fields threading the star could create fractal-like crystal structures, while rotation might shear the lattice into exotic defects. The true end state, whether a perfect single crystal or a quantum glass, remains one of astrophysics' great unsolved puzzles. This glacial transformation isn't just academic. A crystallizing neutron star becomes a cosmic time capsule, its structure encoding information about the universe's expansion rate, dark matter interactions, and even the possible existence of strange quark matter. As the last heat bleeds into space, these frozen relics may outlive galaxies themselves, silent, ultra-dense monuments to the stars that forged them, waiting in the darkness for a future we can scarcely imagine. At the very edge of what physics says should be possible, neutron star PSR J0740+6620 defies expectations by packing an almost unimaginable 2.35 solar masses into its tiny frame. That makes it the heaviest neutron star ever measured, so dense its existence pushes against the fundamental limits of how tightly matter can be squeezed before collapsing into a black hole. To grasp the sheer extremity of this cosmic heavyweight, imagine taking 3 of our suns and crushing them into an object just 24 kilometers wide, smaller than the length of Manhattan. The discovery of this record-breaking star didn't just happen by accident. Astronomers used a phenomenon called Shapiro delay, a subtle distortion in the pulsar's radio waves caused by the gravity of its white dwarf companion, to weigh it with unprecedented precision. As the pulsar's signal passed through the warped space-time around its neighbor, the delay revealed the system's masses like a cosmic scale. The result sent shockwaves through astrophysics. J0740 plus 6620's mass teeters right on the brink of the theoretical maximum for neutron stars, a threshold known as the Tolman-Oppenheimer-Volkoff limit. This star isn't just breaking records, it's rewriting textbooks. Its existence challenges decades-old assumptions about how matter behaves under such extreme pressures. Most models predicted neutron stars couldn't sustain much beyond 2 solar masses without imploding into black holes. Yet here's J0740 defying the odds. Some theorists now suggest its core might harbor exotic states of matter like free quarks or hyperons that provide additional resistance against gravitational collapse. Others propose its rapid spin, nearly 300 rotations per second, acts like a cosmic centrifuge, helping it cling to stability through sheer rotational force. The implications ripple far beyond one stellar oddity. If neutron stars can grow this massive without collapsing, it means our understanding of the strong nuclear force, the glue binding atomic nuclei, might be incomplete. Laboratories on Earth can't replicate these densities. Even particle colliders like the LHC only briefly create conditions a fraction as extreme. J0740 is essentially a natural particle physics experiment, offering clues about how matter behaves where quantum rules and relativity collide. What's even more fascinating is how this heavyweight champion might meet its end. Adding just a bit more mass, perhaps from a stellar companion or a catastrophic collision, could push it past the point of no return. The resulting collapse would trigger gravitational waves detectable across the universe, offering a front-row seat to the moment matter loses its final stand against gravity's inexorable pull. Until then, J0740 plus 6620 remains a cosmic tightrope walker, balancing on the knife's edge between existence and oblivion, proof that the universe always finds ways to surprise us. Most neutron stars cloak themselves in hydrogen or helium atmospheres, but a rare few wear something far more exotic, a shroud of crystallized carbon so dense it might resemble diamond. These cosmic jewelry boxes, detected through their peculiar thermal spectra, challenge everything we thought we knew about stellar atmospheres. When the X-ray telescope Chandra observed neutron star 1154-6208, it revealed surface emissions unlike any typical hydrogen-rich star. Instead, the spectral fingerprints pointed to carbon layers compressed under gravity 100 billion times stronger than Earth. Under such extreme pressures, carbon atoms don't just bond. They're squeezed into lattice structures where electrons behave radically differently than in Earth's diamonds. Simulations suggest these stellar diamond blankets might only be centimeters thick, yet contain carbon crystals with properties we can barely imagine. Some models propose the carbon forms sheets akin to graphene but stacked vertically like pages in a book, creating a material that's both ultra-rigid and bizarrely conductive. The surface gravity is so intense that if you could somehow scoop a teaspoon of this material, it would vaporize explosively the moment pressure was released, unleashing energy equivalent to a nuclear blast. What makes these carbon atmospheres truly fascinating is how they form. In binary systems where a neutron star feeds on a carbon-rich companion, or in ancient pulsars where hydrogen layers have burned away, nuclear reactions at the surface can fuse lighter elements into carbon over millennia. As the carbon builds up, gravity presses it into degenerate states where quantum effects dominate. The resulting diamond rain phenomenon, where carbon crystallizes directly from the atmosphere, might explain thermal emission patterns that fluctuate like twinkling gemstones under X-ray scrutiny. While we'll never mine these celestial diamonds, their very existence reveals hidden chapters of stellar evolution. They're cosmic alchemists' crucibles where familiar elements are forged into forms that defy earthly physics. And each new detection reminds us that the universe's most dazzling treasures aren't found in jewelry stores, but in the graves of dead stars. Einstein's theory of relativity predicted something mind-bending. Massive spinning objects don't just exist in space. They pull the very fabric of space-time around with them like honey clinging to a spinning spoon. Neutron stars, with their insane densities and blistering rotation speeds, take this phenomenon called frame dragging to cosmic extremes. Picture a pulsar spinning hundreds of times per second, its gravity so intense that it twists the surrounding space-time into a swirling vortex, forcing anything nearby to orbit along with the star's rotation. This isn't science fiction, it's measurable physics, and neutron stars are nature's ultimate laboratory for testing it. Back in 2004, NASA's Gravity Probe B mission confirmed frame dragging around Earth with painstaking precision, detecting subtle shifts in gyroscopes orbiting our planet. But Earth's rotation is leisurely compared to a neutron star's furious spin. Around these stellar remnants, frame dragging becomes so powerful it could alter the orbits of nearby asteroids or even warp the paths of light itself. Some pulsars in binary systems exhibit tiny orbital precession, a wobble in their motion that matches Einstein's predictions for just how much a spinning neutron star should drag spacetime along with it. The Hulse-Taylor pulsar, for instance, shows orbital changes consistent with frame dragging so strong it effectively steers its companion star through a spiraling dance in curved space. What's wild is how this effect scales. The faster and more massive the neutron star, the more it distorts spacetime. Millisecond pulsars spinning nearly 1,000 times per second might create frame-dragging vortices visible in their X-ray emission patterns, with photons literally corkscrewing as they escape the star's gravitational whirlpool. Some theories suggest that if you could orbit close enough to one of these spinning monsters, you'd be pulled around so forcefully that time itself would slow down relative to the rest of the universe, a real-world version of the twin paradox, where astronauts near the star age slower than those farther away. But the real magic happens when two neutron stars orbit each other. Their mutual frame dragging creates a cosmic tango, with each star's rotation twisting spacetime so violently that the entire system emits gravitational waves, ripples that subtly shift the star's orbits over millennia. The 2017 detection of colliding neutron stars by LIGO showed this process in its final catastrophic stages, proving that frame dragging isn't just theoretical. It's a dynamic force that shapes the evolution of some of the universe's most extreme systems. So while Earth's frame dragging is subtle enough to require super-sensitive gyroscopes to detect neutron stars where their spacetime warps like a signature, a reminder that in the cosmos, even empty space isn't truly still. It's a fluid, dynamic canvas, twisted and stretched by the spinning skeletons of dead stars, and every pulse of light that escapes their gravitational grip carries the imprint of that distortion, whispering secrets about the fundamental nature of reality itself. For decades, astronomers have faced a cosmic accounting problem. About a third of the universe's expected normal matter, known as baryons, seems to be missing. But what if some of that missing matter has been hiding in plain sight, tucked away inside countless unseen neutron stars drifting between the stars? These dark celestial relics could be the universe's way of balancing the books, quietly locking away masses of unaccounted-for material in the densest packaging imaginable. The missing baryon mystery isn't about dark matter. It's about the ordinary protons and neutrons that make up everything from planets to people. Based on observations of the early universe, scientists predicted how much baryonic matter should exist in the cosmos today. Yet when they tally up all the visible stars, gas clouds, and galaxies, the numbers fall short. The leading theory suggests the rest is hiding in vast, diffuse filaments of warm gas between galaxies, but some researchers suspect neutron stars could account for a significant chunk. Here's why neutron stars are the ultimate cosmic vaults. A single one can contain up to twice the mass of our Sun compacted into a sphere just 20 kilometers wide. Multiply that by millions of potential dark neutron stars, those not pulsing as detectable pulsars or glowing in X-rays, and suddenly you've got a stealthy reservoir of baryons that telescopes have overlooked. Unlike black holes which swallow matter permanently, neutron stars preserve baryonic mass in a form that's technically still part of the universe's ordinary matter budget, just locked away under extreme conditions. The math gets even more compelling when you consider how many neutron stars might exist unseen. Current estimates suggest the Milky Way alone could harbor hundreds of millions of these stellar remnants, but we've detected fewer than 3,000. Many could be too cold, too distant, or oriented so their beams don't sweep past Earth. Some might lurk in the galactic halo or between galaxies, ejected by ancient supernova into the cosmic void. If even a fraction of these dark neutron stars exist, they'd represent a substantial baryon cache, potentially enough to close the gap in the universe's missing matter inventory. Detecting them, however, requires clever indirect methods. One approach looks for gravitational microlensing events, brief brightenings of background stars when an unseen neutron star's gravity bends their light. Another studies the subtle way these invisible objects might perturb the orbits of visible stars or gas clouds. Recent advances in infrared astronomy could also help spot cold neutron stars by the faint heat they still emit, while next-generation gravitational wave detectors might catch the ripples from their collisions. The implications stretch beyond bookkeeping. If neutron stars are indeed hiding a significant portion of the missing baryons, it would reshape our understanding of how matter cycles through the cosmos. These stealthy remnants could be the universe's ultimate recyclers, hoarding normal matter forged in the Big Bang and stellar furnaces, then releasing it back into the interstellar medium via collisions or slow evaporation over billions of years. It's a cosmic game of hide and seek, where the hiders are city-sized vaults of degenerate matter, and the seekers are physicists armed with telescopes and gravitational wave detectors, each new discovery bringing us closer to solving one of astronomy's most persistent accounting puzzles. When gravitational wave detectors LIGO and Virgo picked up a strange ripple in spacetime on August 17, 2017, astronomers had no idea they were witnessing history in the making. The signal, designated GW170817, didn't arrive with the deep, booming echoes typical of black hole collisions. It was more like a high-pitched cosmic chirp lasting just 100 seconds. What made this detection revolutionary wasn't just the event itself, but how it unfolded. For the first time, humanity heard two neutron stars collide through gravitational waves nearly 2 seconds before telescopes saw the explosion in light. That brief delay marked the dawn of multi-messenger astronomy, a new era where we could study cosmic cataclysms through both space-time vibrations and electromagnetic radiation. The gravitational wave signal told scientists exactly where to look. Unlike black hole mergers, which vanish without a trace, neutron star collisions were predicted to produce fireworks, specifically Kilonova, explosions that forge heavy elements like gold and platinum. Telescopes around the world immediately swung toward the patch of sky LIGO identified, and there it was, a pinprick of light in galaxy NGC 4993, 130 million light-years away. The Kilonova's glow matched the gravitational wave signal's timing and location with uncanny precision, confirming theories that had waited decades for proof. But the real magic lay in the details, the way the event's gravitational waves revealed the star's masses and spins, while its light spectrum exposed the chemistry of their wreckage. Together, these messengers painted a complete picture no single observation could achieve alone. What's astonishing is how differently these signals traveled. Gravitational waves race through the universe unimpeded, warping spacetime itself as they pass. Light, however, gets delayed by interstellar gas, magnetic fields, and even the expansion of the cosmos. That 2-second gap between the gravitational wave arrival and the first gamma-ray flash wasn't a glitch, it was physics in action, proving Einstein right yet again. Later observations showed even more delays. X-rays peaked 9 days post-merger, while radio waves took weeks to brighten, each wavelength revealing another layer of the aftermath. This event didn't just validate multi-messenger astronomy, it redefined it. Suddenly, gravitational waves weren't just curiosities, they were early warning systems directing telescopes to cosmic explosions they might otherwise miss. The Kilonova's light, in turn, decoded the merger's elemental output, showing how much gold, platinum, and uranium had been forged in the collision. Together, they proved neutron star mergers are the universe's primary heavy element factories, solving a mystery that had puzzled scientists for decades. The legacy of GW170817 lives on in every major observatory today. From neutrino detectors to radio telescopes, astronomers now coordinate across disciplines, knowing the next cosmic chirp could unlock secrets about dark energy, quantum physics, or even new states of matter. It's a reminder that the universe speaks in many languages, and sometimes you need to listen before you look. Magnetars don't just bend the rules of physics, they rewrite them in antimatter. These ultramagnetic neutron stars generate fields so powerful they can spontaneously tear the fabric of the quantum vacuum apart, creating pairs of electrons and their antimatter counterparts, positrons. Picture a magnetic field a quadrillion times stronger than Earth, so intense it distorts empty space itself. Under these extreme conditions, virtual particles that usually flicker in and out of existence too quickly to detect get yanked into reality, their brief quantum dance frozen into permanence by the magnetar's overwhelming grip. The evidence comes from fingerprints in the cosmos. Space telescopes like Integral have detected gamma-ray signatures near certain magnetars that match positron annihilation, the explosive moment when a positron meets an electron and both vanish in a flash of energy. These 511 kiloelectronvolt emission lines, first spotted near the galactic center, appear in magnetar environments too, suggesting these stars aren't just cosmic dynamos but antimatter factories. Some theories propose that twisted magnetic field lines near the star's surface act like particle accelerators, boosting electrons and positrons to relativistic speeds before they collide and annihilate in bursts detectable across interstellar distances. What's wild is how this process defies earthly physics. In labs, creating even microscopic amounts of antimatter requires massive particle colliders and staggering energy inputs. Magnetars do it effortlessly, their magnetic fields essentially combing through the quantum foam and plucking out positrons like apples from a tree. The scale is mind-boggling. Some models suggest a single magnetar flare could produce more antimatter in seconds than humanity has ever manufactured. These antimatter surges might even solve a cosmic mystery. Astrophysicists have long puzzled over the excess positrons detected in Earth's vicinity by instruments like the Alpha Magnetic Spectrometer on the International Space Station. While some come from pulsars, magnetars could be the missing contributors, their distant annihilation events seeding galaxies with positrons that drift across light years before meeting their end in our detectors. But the real magic lies deeper. If magnetars can wrench particles from the quantum void, they're not just stellar objects, they're portals to testing quantum field theory under conditions no lab could ever replicate. Every positron annihilation line is a clue, a whisper about how spacetime itself behaves when pushed to the breaking point. And with each new detection, these magnetic monsters remind us that the universe's most extreme environments aren't just destructive, they're creative, forging the building blocks of reality itself from the raw chaos of twisted spacetime. Some neutron stars don't just exist in binary systems, they consume them. Meet the universe's ultimate cosmic predators, Black Widow and Redback pulsars, stellar remnants so voracious they slowly devour their companion stars, leaving behind nothing but a ghostly trail of ionized gas. These aren't quiet partnerships, they're stellar horror stories where a spinning neutron star's relentless radiation strips away layers of its neighbor like a relentless cosmic sandblaster. Take PSRB 1957+20, the original Black Widow pulsar discovered in 1988. This millisecond pulsar spins 622 times per second, whipping its magnetic field into a frenzy that bombards its companion with particle winds moving near light speed. The victim, a star roughly 1% the mass of our Sun, is being evaporated at a rate that would vaporize an object the size of Jupiter every 100 million years. Hubble images reveal the aftermath, a vast cloud of plasma stretching tens of astronomical units behind the system, like the tail of a comet forged from stellar carnage. But the brutality doesn't stop there. Redback pulsars, named for the equally deadly Australian spider, take this destruction a step further. These systems often feature companions bloated by the pulsar's heat, their outer layers puffing up into distended atmospheres that the neutron star's gravity eagerly steals. Some redbacks, like PSRJ 1023+0038, alternate between two nightmarish states, sometimes gorging on gas in bright X-ray feasts, other times flaying their partners with gamma-ray winds. The companion stars in these systems are literally being cooked alive, their outer layers stripped to expose cores that glow with eerie blue heat under the pulsar's relentless assault. What's chilling is how these zombies reshape their victims. The intense radiation doesn't just ablate the companion star, it warps its very structure. Tidal forces stretch the star into a teardrop shape, while X-ray irradiation heats one hemisphere to tens of thousands of degrees, creating a grotesque day and night side. Some companions are whittled down to planetary masses, their remains so tenuous they resemble comets more than stars. Others, like the companion to PSRJ 1311-3430, are reduced to a mere smear of ultra-dense helium, a stellar core stripped bare by billions of years of abuse. Yet even in this carnage there's cosmic irony. The same process that dooms these stars also re-energizes the zombie pulsars themselves. As they feast, stolen gas transfers angular momentum, spinning the neutron stars up to millisecond speeds. It's a twisted form of stellar resurrection, the dead reviving themselves by consuming the living. And when the meal ends, the pulsar doesn't just move on. Its magnetic field, reinvigorated by fresh plasma, can suddenly switch back on, lighting up the corpse of its former companion in a final, flickering glow. These binary horror shows aren't just macabre curiosities, they're cosmic laboratories. By studying how black widows and redbacks evolve, astronomers can trace the lifespan of binary systems, the physics of mass transfer, and even the origins of mysterious fast radio bursts. The trails of ionized gas they leave behind act like interstellar breadcrumbs, marking paths of destruction that could last longer than the galaxies that birthed them. So while these zombies may be the villains of their own stories, they're also storytellers revealing how the universe recycles matter, energy, and even entire stars in its endless, violent dance. From their origins in catastrophic supernova to their role as cosmic alchemists forging gold in violent collisions, neutron stars, especially those in the universe's farthest reaches, have shattered our understanding of physics. These stellar remnants pack suns worth of mass into city-sized spheres, where matter crushes into quantum soups of neutrons, quarks, or even crystalline nuclear pasta. Their magnetic fields could dismantle atoms from light years away, their gravity bends space-time into knots, and their spins rival kitchen blenders at full throttle. Some, flung across galaxies at millions of miles per hour, become intergalactic fugitives. Others, like the ancient PSRJ 2144-3933, pulse steadily for billions of years as silent witnesses to cosmic history. The most distant neutron stars, glimpsed across 13 billion light-years, are time capsules from the universe's infancy. Their extreme conditions recorded in redshifted pulsars and gravitational waves challenge how quickly stars could form and die after the Big Bang. They've revealed themselves as nature's ultimate laboratories, where matter exists in states we can't replicate on Earth, and where the laws of physics are pushed beyond recognition. From frame-dragging vortices to antimatter-generating magnetars, these objects don't just follow cosmic rules, they rewrite them. So, which fact left you awestruck? Was it the Black Widow pulsars eviscerating their stellar partners, or the Kilonova scattering golden stardust across the cosmos? Maybe it was the whisper thin atmospheres hotter than the sun, or the gravitational waves singing of collisions older than Earth itself. Drop your favorite in the comments. We're obsessed with these cosmic enigmas too. And if you crave more deep dives into the universe's wildest mysteries, hit subscribe. The cosmos has endless secrets to reveal, and we're just getting started.